Very good morning, Dr. Vivek, sir.
Good morning.
Uh, can we start with that presentation test? You wanted to test.
Yeah, let me share. Give me a second.
Good morning, sir.
So, are you able to see the entire screen?
Yeah, sir, we can see the ribbon of your. Please put it on the full presentation mode.
So, this is in full presentation mode, but let me try to do this in a different way. Do you see the entire screen now?
Yes, you can see the entire screen.
All right.
Please,
So,
sir.
yeah, and let me just check if you can see the movies as well.
Yes, yes, they are moving. And now I can see the slide number two.
Okay.
Yeah, the animation is also here.
And is there a lag? So, I'm going to play the second animation now.
Yes, we can see it. The colors are changing.
Okay. Perfect. And you see the entire screen.
Yeah, we are seeing the entire screen.
Okay.
So within few minutes, we shall be starting with the session at 11 sharp.
Okay.
Yeah. Yeah, we need. कोई प्रॉब्लम तो नहीं कोई प्रॉब्लम तो नहीं है हैं? नहीं बस Vivek sir,
Yeah.
I just wanted to know that can we record your presentation and or not?
Um, yeah, I
It's up
think
to.
most of the things are published, so should be fine.
Hold on, it doesn't.
Uh, I think it excluded some of the unpublished.
Okay. Dear participants, uh, very good morning to one and all. And I once again welcome you to the day two of our online short-term course on contemporary materials technology. Uh, Let me reintroduce Dr. Vivek Sharma. Dr. Vivek Sharma is an associate professor of chemical engineering at University of Illinois, Chicago. Dr. Sharma pursued postdoctoral research in mechanical engineering at MIT, received PhD in polymer science and engineering with minor in physics, material science and engineering in 2008, MS in chemical engineering with minor in non-linear dynamics and chaos in 2006 from Georgia Institute of Technology, MS in Polymer Science from University of Akron in 2003, B.Tech in Textile Technology from IIT Delhi in 2001. His research interests include rheology and processability, DOS, rheometry, polymer physics, bubble drop, jets, emulsions and foams, biophysics and protein science, structural color, adhesion and wetting, food science and molecular engineering. Dr. Sharma's soft matter ODS lab, that is optics, dynamics, elasticity, and self-assembly laboratory, focuses on molecular science and engineering of formulation, multi-component complex fluids. His group develops distinctive experiments and theory for investigating interfacial flows and instabilities, surface forces, optics, self-assembly, and nonlinear viscoelasticity of industrial and biological soft matter. Dr. Sharma was selected as a distinguished young rheologist by TA Instruments in 2015, won the 2017 College of Engineering Teaching Award by UIC, and was awarded a 3M Non-Tenured Faculty Award in 2019. Dr. Sharma has published more than 100 research articles in peer-reviewed journals and international conferences. He has 2,000 plus Google Scholar citations and H index of 20 plus till date. Apart from his academic contributions, he has deep interest in poetry and writing. Dr. Sharma's first book of verse, The Saga of a Crumpled Piece of Paper, was shortlisted by News India Young Writers Award in 2011. His work in English appears in Atlanta Reviews, Batu, Mythium, the Cortial Reviews, Scotland Review, News India, Reading Hour, among others, while his Hindi articles and verses appear in Divya Himachal, Hindi newspaper India, Himachal Mitra, and Agala. Let us now welcome our guest of honor and today's speaker, Dr. Vivek Sharma. And now I hand over the session to Dr. Vivek Sharma to start it with his speech.
Thank you, Rajiv, for that very nicely detailed introduction. Good morning, everyone. It's my distinct pleasure to be sharing our work on macromolecular engineering of formulations. The work that I'm going to talk about today was primarily carried out by Yelena Dinic, who was an excellent PhD student, went on to win Parent Award, which is probably the highest award you can win as a polymer physics student. It's given by American Physical Society, and also won a couple of other awards, including one from AACHE. And now she's a postdoc in University of Chicago and Argonne National Lab. Naili started out as an undergraduate with me and worked with Elena initially, and defended her PhD only last month. And some slides would have contributions from Karina Martinez, who's a current PhD student. The work that I'm going to describe today hopefully would convince you that a lot can be done with few resources. A lot of experiments that I'll describe are done with the cheapest polymer, polyethylene oxide, and many polysaccharides that sometimes you can find in regular stores as thickeners or food additives. And many of the experiments are done in the most inexpensive solvent you can imagine, and that's DI water. And the key to our investigation is understanding of how surface tension drives formation of these liquid necks that can undergo capillary pressure driven thinning or capillary driven thinning and breakup. So if you want to imagine what I'm showing you here, this is essentially similar to formation of drop from a nozzle. And when I refer to necks, this is the neck that breaks before a drop separates from the nozzle. And it's the understanding of how to control the lifetime of this neck thinning dynamics, or how do you control neck thinning dynamics, that's essential to um, design of lots of cosmetics, paints, inks, food formulations. Almost anything that can be dispensed from a bottle requires an understanding of drop formation, dispensing, or how surface tension flows drive this neck thinning process. The work today is funded more or less by National Science Foundation, PPG. It's a world's biggest paints and coatings company. The 3M award. 3M is again one of the big consumer products company, and does have a lot of interest in understanding some of this behavior in context of stickiness as well as spraying um, formulations. And Motive Foodworks recently funded us to apply this knowledge in design of meat alternatives and milk alternatives, or future foods that would be sourced from plants rather than from animal sources. So the talk today is going to more or less focus on the idea that's enshrined on the left-hand side. This movie compares drop formation of water and a polymer solution. So you see two drops. This is a high speed image slowed down from initial 20,000 frames to around 30 frames a second. On the left hand side is water, and in case of water, try to play this again, you see the neck thins rather quickly and a satellite drop forms. Whereas when we add polymer only in a quantity that's around 0.028%, so it's almost a small pinch into a whole bucket. That is enough to delay the neck thinning, cause formation of the stringiness. And this delay in pinching or formation of stringy filaments is important thing to characterize when we are trying to make inks, sprayable paints, insecticides, pesticides, anything that can be atomized, including all your perfumes, cosmetics that are atomized, nasal sprays that are used for pharmaceutical applications. And in all these applications, the polymers are sometimes picked because they help in final deposition, or they might form the film, or they might modify the flow behavior, which in context of non-Newtonian fluids is referred to as rheology. And I've included around 5 or 6 slides in the beginning to describe some of the terms that I'll be using again and again. And I'm going to assume that almost everyone here is familiar with surface tension. So essentially, if you want to think about surface tension, there are two ways to think about surface tension. One way to think about surface tension is anytime I create a surface, I have to break a certain number of bonds, and that costs a certain amount of energy per unit area, surface energy per unit area, and that is surface tension. Another way to think about surface tension is in terms of force and force per unit length. And this force per unit length, then if you divide by another length scale, in this case, a radius of the liquid neck, then that gives rise to a pressure that's known as Laplace pressure or capillary pressure. So based on this definition, where sigma is surface tension of water is very high. It's almost 2 or 3 times surface tension of all the typical organic fluids, and at room temperature it's going to be 72, as long as you're looking at pure water. So when the liquid neck forms, as the R becomes smaller and smaller, the capillary pressure becomes larger and larger, and this pressure driven flow drives fluid away from the neck. So in some sense, the capillary pressure can strangle the neck, and that understanding how material properties control this time scale over which the neck breaks is important for many applications, and I'm going to discuss this in great detail today. Another aspect that our group really looks at, which I'm not going to cover in any detail today, or I'm just going to refer to in maybe a couple of slides, is understanding of foam stability as well as foamability. In context of foams, one of the key things that is important is presence of soaps or detergents, and these are surface active molecules that can go to liquid air interface. And these surfactants or soap molecules typically have they're made from fatty acids, so they're made from oils, maybe from coconut oil or palm oil or oleic acid. And in those cases, the tail is oil-like. Hence, when you add surfactants to water, the surface tension goes down from water surface tension to almost oil-like surface tension, and this helps in wetting. And yesterday I mentioned this, that these surfactants can form self-assemble and form micelles that allows you to wash away oil-soluble dirt, and in case of digestion, bile salts can form those micelles to allow carrying away of fat. So, in some sense, we again return to this problem of how surface tension-driven flows arise in foams. And here I'm showing you a foam created in a petri dish. So again, this is the cheapest experiment possible. This is regular soap solution. And what you're visualizing here are single foam films. Where they intersect with each other are thicker regions called plateau borders. And once you let this go, you can see these interference colors. These colors you can also see in soap films. We refer to such colors as structural colors. Similar colors arise in some butterflies and beetles. And these are due to thin film interference. And as the film thickness changes, the interference intensity and these colors change. And by really following the change in colors and interference intensity, we can map out how thickness changes over time. And we can do this measurement right down to a nanometer thickness. So you can get molecular scale information of intermolecular forces by really studying just thin film drainage. And here I'm going to show you what happens as a typical foam dies. Okay, so let me restart this. Okay. Is the presentation still visible?
Yes, visible, sir.
Okay, okay. So one of the key quests for my group has always been to understand and control interfacial and nonlinear flows. But the story today is focused on formulations, and when I talk of formulations, I'm essentially thinking of anything ranging from cosmetics, which could include things like shampoo, conditioners, as well as nail polish, and a whole variety of materials that typically have small amount of polymer added, either to modify rheology. In case of conditioners, small amount of polymer is added so that it can go and coat your hair to make it silky and smooth. So that film that's formed by a small amount of polymer is important in getting the silky behavior, but addition of polymer will change the flow behavior, and it's important to understand that flow behavior also, not just from the perspective of what happens when you put this shampoo or conditioner into the palm of your hand, but also when you fill the bottles. And in industry, you have to fill thousands and thousands of bottles as fast as possible. Likewise, when we think about paints, foods like mayonnaise or yogurt sometimes has this stringiness or ropiness. And in many of the commercially available yogurts, that stringiness, or even in ice creams, is tuned by addition of polymers. And how do you characterize the influence of polymers is going to be a message that I'm going to get across over the period of my talk. So I think of my group as a group that focuses on optics, dynamics, elasticity, and self-assembly. The talk today is going to focus on aspects that are directly relevant to this images that you see on the left-hand side. And the key questions are not only about drop formation, but what choice of polymer molecular weight, concentration, and so on influence a large number of applications where it's desirable to control drop formation dynamics, it's desirable to control the flow behavior. I mentioned briefly that our group also spends a fair bit of time and effort on understanding foam film stability, and in some sense, both these key projects involve interfacial and nonlinear flows. They involve questions that are related to hydrophobicity and charge effects, and I mentioned some of these yesterday. And these are all rather practical problems, but we pursue them with eye on some very fundamental questions about polymer science on the left-hand side and surfactant science on the right-hand side, as well as fluid mechanics. So in the first 6 years or so of my tenure at UIC, we try to focus only on either polymer solutions or on surfactant solutions, whereas in the last year or so, with also motivated by a number of broader problems in environment, health, food, and so on, and the funding that has been coming from industry, we are now motivated to think about multi-component complex fluids. And my overall quest is going to be to use all the information that I'll provide to you today is going to be helpful in creating meat and dairy alternatives, where we'll use the knowledge of how polysaccharides and proteins behave to maybe get kind of food materials that have the nice texture, mouthfeel. So an ice cream that is not based on milk, a yogurt that is not based on regular milk but on plant-based proteins is one of the future goals. Or one of the current goals is to try to help in designing water-based paints and cosmetics, which have minimal amount of volatile organic compounds, and this requires an understanding of how different ingredients contribute to drop formation, film formation, flow behavior, and that's something we'll look at in great detail today. All right, so I'm going to venture to define some of the terms that we'll be repeating again and again, and maybe the next 5 or 6 slides are at a very introductory level, so you can think of these as a quick revision. So rheology is a study of response to deformation. And when we think about response to deformation, we can define it in the following sense. We poke a material and then we measure the response to either an applied stress or an applied strain. So in the schematic here, if we think of a control volume, and that is a cube, and we apply a force on the top surface in x direction or x1 direction, then this force per unit area can be labeled as stress, and that stress is causing the shearing deformation, and shearing deformation can be quantified as strain, which is this S divided by the height, or a strain rate, in which case we take derivative of the strain. So the key idea that we want to remember is that when we apply a particular stress and we observe a particular strain or strain rate, there is typically a proportionality that is based on material properties, and understanding what those material properties are in context of design of new technologies as well as processing is one of the key aspects of molecular engineering or formulations. There's going to be a fair bit of mention of non-Newtonian fluid mechanics and how we characterize rheological response, especially extensional rheological response. And then hopefully through those discussions, you'll see how we combine these ideas, macroscopic measurements and molecular or macromolecular understanding to come up with new design principles, to come up with better formulations or utilize less material to get the same consumer experience of flow behavior. So if you go back and look at the key definitions for solids, stress is directly proportional to strain. This applies for both the tensile stress and applies for the shear stress. And in case of solids, this law is attributed to Hooke, whereas in case of liquids, perfect liquids, whenever we apply a deformation, we can't really get a strain, we get a strain rate because in response to stress, fluids flow. And in that context, the resistance to flow is characterized as viscosity. This is something we teach undergraduates, graduate students in all different courses. and I think is as familiar as can be to most chemical engineers, material scientists, mechanical engineers. What is sometimes less familiar is the idea of non-Newtonian and viscoelastic response, and here are two illustrative examples. So the upper example is example of an aloe or jello or cream, and in many creams, and even in things like toothpaste or in ketchup, what happens is if you let it sit, if you let that material sit, even in foam, if you let it sit, it maintains its shape, it does not flow, it looks as if it's solid. But in this case, if we even turn an inclined plane above a certain angle, gravity induces enough stress that this can start to flow. Of course, many of you probably are familiar with this in context of trying to get ketchup to flow, where we can do shaking, or you can just allow the weight to produce enough stress to exceed the yield stress such that it starts flowing. The lower image illustrates something that sometimes we allow kids to play with silly putty, and silly putty, if you smash it against a wall or against a floor, it bounces like an elastic ball. So at short deformations or at fast deformations, it behaves almost like an elastic material. Whereas if we let that silly putty ball sit on a surface over a period of time, it just loses shape and in fact flows like liquid. So there is something about what amplitude of stress can do in terms of transforming behavior from elastic to viscous, and of course about either time scale or the rate of deformation that can sometimes give you more elastic or viscous behavior. And that is an attribute of a lot of foods, cosmetics, daily use materials that are classified as complex fluids. And complex fluids can show both non-Newtonian and viscoelastic effects, which we'll discuss as we go along. So, Newtonian fluids, what Newton said was the stress is directly proportional to shear rate, and proportionality constant is viscosity. It's a constant. So if we measure viscosity as a function of shear rate, and this can be done simply by placing fluid between two parallel plates or between uh, cone and plate on something called a rheometer. It's a device that has a motor that can move one of the plates, and it has a transducer that measures the stress that's imparted to the other plate. And if you can measure both the stress and rotational rate, and you know the distance between the plates, it allows you to get shear rate. And from the ratio of stress to shear rate, measure stress for an applied shear rate, you get viscosity. For Newtonian fluids, viscosity is a constant. For many non-Newtonian fluids, you can see either an increase in viscosity. This is something that can happen for cornstarch. So if you take cornstarch, mix it in water, and fill maybe a small pond with cornstarch solution, what you'll find is if you try to walk on that pond of cornstarch solution, you're doing a slow deformation, viscosity is going to be low, and you'll sink into this pool. If you try to run on it, the deformation rate is high, and then the material acts almost like a solid, and you can really run on this liquid, which is formed by adding just cornstarch to water. Um, this is something that's important to know if you're trying to mix some of these complex fluids. And in this particular case, if you try to go to higher and higher rates, it's not going to help, and your mixer might jam. Many polymer solutions are pseudoplastic, or they are shear thinning, which means as you push on them, as you increase either the pressure that you apply or you increase the shear rate, the viscosity drops considerably. And they sort of start to become more mobile, or they can flow more easily. So there are four key rheological phenomena that people try to be at least aware of or study. The first one is shear thinning, which I just mentioned. Viscosity decreases with increase in shear rate. This is something that most of you are familiar with when you apply butter to a toast. As you apply the knife to butter, there's a very high shear rate in the space between knife and the bread. And in that shear rate, butter, which otherwise is solid-like, converts to almost liquid-like thing and can be spread out easily. I mentioned silly putty and gave you an example of how it behaves like a solid at short deformation rates, like a liquid at large times. And so this is something that's related to modulus, which is function of both time and the applied strain. And we'll mention stress relaxation in a bit, in a slide or two. The other fascinating thing that happens when you have polymer solutions on some of these viscoelastic fluids is if I take a rod and rotate it in a pool of fluid, for a Newtonian fluid, centrifugal forces push the fluid away and you get a dip next to the rod. And this is a problem that we give to undergraduate students in typical transport phenomena classes. However, if we take the rod and spin it in a polymeric solution for high molecular weight polymers or for reasonably high concentration of polymers in solvent or even polymer melts, what you see is rod climbing. And this rod climbing can again uh, play an important role, especially when you're trying to mix faster and faster. Rod climbing could short your motor again. So this is an example of normal stress effects, and what that means is if I try to make measurement in a cone and plate geometry, in addition to resistance to a rotational deformation, as you rotate one of the plates, what you'll find is this normal stress will try to push the plates apart, and that can be measurable too, and can be done on expensive torsional rheometers that can be obtained from, say, T Instruments and Anton Parr and Melbourne and other established companies. There's a fourth example here, which is somewhat less studied, but is going to be an important part of my presentation today, and that's the idea of extensional thickness. So I'm sure many of you siphoned fluid out of a container, and when you siphon a fluid out, if it's a Newtonian fluid, to siphon a Newtonian fluid out, you really have to have your plastic, or you have to have your tube, rubber or plastic tube, inserted into this liquid. And as soon as you pull it out of the liquid, of course, the flow stops. Interestingly, for polymeric liquids, if you start siphoning fluid out, even though your hose or your tube is no longer dipped into the liquid, this liquid can really take some extensional stress and has a pretty high resistance to this kind of stretching deformation. And that allows you to get this tubeless siphon effect. This is a fascinating effect if you've not seen it before. And this is the same effect that is also responsible for the delayed pinch off or delayed breakup of a liquid neck, as we'll discuss in coming slides. So Newton and Hooke were the two people who came up with the idea of what a solid is, what a liquid is, and they both didn't like each other too much. So they would have been appalled if they had survived to see Maxwell take their individual models and combine them into a model for what is the simplest model for viscoelasticity. So in the simplest model for viscoelasticity, Maxwell combines a dashpot, which has viscous response, with a spring that has a elastic response. And when you combine these together in series, it turns out that you end up with a constitutive model that's called Maxwell model. And now if you apply, if you poke, you apply a step strain, you just pull it by a certain amount, and then you stop, then this, once you stop, the gamma dot becomes zero, and you're left with this simple differential equation. If we solve this differential equation and define modulus as stress over strain, this gives you essentially the idea that if you are able to measure stress as a function of time, the amount of stress required to maintain that strain is going to decay exponentially. And the decay constant is this time scale called relaxation time. This relaxation time, in some sense, is the ratio of viscosity to modulus, and so contrasts the viscous and elastic effects. All right. So a Newtonian fluid has no memory as soon as you stop the flow. As soon as you stop the deformation, everything stops. Whereas in Maxwellian fluid, if you apply a certain strain and then you stop, it can recover part of the deformation. There are other viscoelastic effects in addition to rod climbing that I mentioned and tubeless siphon flow that was mentioned. So some of these include instabilities that can arise in Taylor-Couette cell. There are some edge fracture instability that can arise when you're making measurements on torsional rheometer. And if you do any of these measurements, be careful to be aware of where these instabilities arise. One of the other fascinating place where viscoelastic effects become important is when you pump something out of a nozzle, and this is something important for, especially for 3D printing. In 3D printing, the governing idea is that you want to get features of a certain size deposited at the right place. And usually the feature size is set by the nozzle size through which a liquid is pumped. For Newtonian fluids, as a liquid comes out of a nozzle, there is a tapering and the size of actual deposited layer is thinner than the nozzle size. Whereas for polymeric fluids, you can have a release of stresses and there can be die swell, and that makes designing precision deposited materials or injection molded materials that much harder. And there are strategies to avoid or control or understand extruded swelling. All right. So now we are at the stage where we can really dive into the quests that I am after. So when we go to industry, most people try to design formulations using this kind of map. This kind of map is used for paints, for inks, for cosmetics. And even if you think about biological fluids like blood or saliva or mucus, they all share this attribute. Most of them are shear thinning materials. They're expected to have a high shear viscosity at low rates that allows them to stick to a substrate, stick to wall if it's a paint, stick to and not flow too much if it's a cosmetic that's being poured into your hand, maybe a hand cream or a lotion or shampoo or conditioner. It's supposed to pile up on your hand. However, when you are trying to dispense it or spray it, it's desirable to have as low viscosity as possible. And that, of course, is something you've also seen in toothpaste, where you squeeze on the tube, it becomes more mobile and comes out. But once it's on the brush, it recovers its high viscosity and stays on the brush without really flowing away. So most of the time people think about shear thinning and they design everything based on shear thinning. And the key idea that I'm going to emphasize again and again is this measurement is not enough. Materials that have same shear thinning behavior or similar shear thinning behavior can be quite distinct in terms of processing, in terms of additive manufacturing, especially if extensional deformations are involved, especially if drop formation is involved. And I'll discuss why in coming slides. This is a list, a laundry list of different shear rates that are encountered during processing and how people design materials to have the appropriate viscosity, depending upon whether you're designing medicines, paints, printing inks, foods, or cosmetics. And it's a good summary of how processing parameters are well known and how people design compositions to give you the right flow behavior. All right. So in a lot of applications that I'm interested in, paint forms a pretty good example of a multi-component system. And paint or ink, you usually have a pigment, you have a polymer, and you have other additives. And as I just said, there's a range of things that we need to control for. We desire high viscosity to prevent pigment settling at low shear rates, whereas when we are really using the paint, either by using a brush or a roller or by spraying it, in this case, the deformation rates are high, and it is desirable to have low viscosity that leads to less power consumption. And if you're really using a roller and doing this yourself, lower viscosity will mean that you'll get tired, or you'll not get tired that easily. So understanding the role of polymers in manipulating the flow behavior is a key aspect. And this is important not just for paints, architecture paints, but also for design nail paints. Just like architecture paints, nail paints also tend to have, they're designed to have similar shear thinning behavior. What my students did in the last few months is they took around 15 different nail paints from three different companies and measured not just the shear viscosity. Here is shear viscosity for all those paints, nail paints, nail lacquers, if you will. Most of them are shear thinning, as you can see. They have some variation in their absolute values of viscosity, but there's very little variation when you compare nail polish from the same company. So they keep similar viscosity versus shear rate profile, and that allows them to save a lot of headache in terms of changing processing conditions when you go from making one color shade to another color shade and so on. Most of these nail paints have nitrocellulose as a polymer additive, and they have some organic solvent that evaporates, which is why when people use nail polish, you can smell, and there's a very strong smell of volatile organic compound. And there's some motivation now to replace this with aqueous based nail paints. Here we were interested mostly in showing that even though um, there are there's a accounting for pigment settling to brush drag through through designing shear viscosity versus shear rate plots. In the actual application, especially when you go to applying nail polish on nails, and my students did experiments like this for each nail paint, um, and in formation of when you pull out, say, a brush from the container, there's always formation of these liquid necks, and those liquid necks, as they break over time, that flow behavior is not something that is captured in these measurements. It's not captured for two reasons. The actual deformation rates during brush application are typically very high, that cannot be reached with a typical torsional rheometer, commercially available rheometer. And there's also deformation modes that cannot be realized in a commercial torsional rheometer. All right. So in these contexts, what we is really important to understand is drop formation physics. And it's very well known that addition of a very small amount of polymer, so 100 ppm, 100 parts per million of polymer, is able to change drop size distribution drastically. So this change in drop size distribution is important for jetting and spraying or atomization applications. It's also important in case of inkjet printing, where sometimes polymer is added because it can eventually form a film once a deposit is made. And if we add a fair bit of polymer, it allows you to make fibers, and these fiber spun mats could be used to design non-woven matrices for um, wound gauges, or even making PPEs or membranes and so on. So what we are most interested in is understanding the influence of added polymers on pinch-off dynamics, jetability, spinability, sprayability, and stickiness, and how these also affect dispensing behavior. Now, if I look at a liquid jet issuing out of a nozzle, and most of you have seen a liquid jet every time you turn a tap on, what you can visualize if you had access to a high-speed camera, or in this case, I use strobe imaging that allows a time resolution of a microsecond. Here is a water jet, and as this water jet issues out of a nozzle, eventually surface tension-driven instabilities arise, which cause the neck to have the sinusoidal instability that results in formation of droplets. You can see very nicely there's a satellite droplet forms, there's a large primary droplet forms, and as you examine this movie, you might also see that before pinch off, there's a very nice cone that forms, and that cone that converts into the satellite drop. If we add a small amount of polymer, 100 ppm or a few hundred ppm, that changes this breakup dynamics completely, and now you don't have any of those satellite drops, and pinching takes maybe slightly longer. If you can avoid satellite drops, that would save a lot of money when you're trying to spray paint things, and it also saves a lot of extra fertilizer or insecticides and pesticides that get blown away because the drop size is too small, so they can't really land on the plant and lead to all kinds of pollution. So it's important to understand how to add small water polymer to control atomization, sprays, fiber formation, jetting, spraying, and that has been motivation for us in many applications. One of the key ways in which, again, this neck thinning dynamics and influence of polymer can be observed is by doing a simple thumb and finger test. And if you place fluid between thumb and finger and stretch it, and this is an experiment done with saliva here, you see that there's a certain perceived stickiness that is manifested as delayed neck thinning dynamics or delayed pinch off. So if you wanted to design artificial saliva, one of the things you need to do is to have this kind of same stickiness. And it's not important or it's not enough. It's important, but it's not enough to characterize as a shear rheology response. There's a large number of applications that involve free surface flows or that involve formation of liquid necks. And this is something that has become even more important in context of additive manufacturing. So one example here is of gravuary printing. This could be used for printing everything from newspapers to photovoltaic devices or electronic devices to t-shirts. And in most of those cases, you have a coating fluid bath. There's a pattern that is to be transferred to elastic web, which could be paper or plastic or textile. And this transport involves formation of these kind of liquid necks or liquid bridges with these necks. That liquid bridge stretches over time, and it's important to control formation of satellite drops or avoid them and maximize the amount of ink transfer. Likewise, when you want to coat paper, for example, we had a project with Dow to figure out how silicone coats paper, and this paper is the parchment paper that's sometimes used in cooking, keeping cookies, baking cookies, and then you can remove those cookies away from paper easily because of non-sticky nature of the plastic. In those cases, it's desirable to control what is known as misting. So again, as entrained liquid is being transferred to the elastic web, there's a formation of liquid sheet that can break into liquid cylinders, and these liquid cylinders again undergo surface tension driven instability that can cause formation of droplets, and these droplets can be health hazard for people working in that industry. So as it turns out, in both these cases, there are formation of either a stretched liquid bridge with a neck or cylinder that converts into a sinusoidal shape that has again a liquid neck. And in these necks, as the liquid is being squeezed out, the flow field is such that a control volume will get stretched in the direction of flow. Such flows are called extensional flows. And those flows are going to be very important, especially when free surface flows or this kind of liquid transfer is involved. Similar flows also arise every time you coat something, dip coat something, or deposit something on a surface. And in this case, the additional extensional flows arise because as you approach a free surface, the control volume gets stretched again. So understanding the response to extensional flows is quite important in all these scenarios. And yet, not that many people focus on it. So if we now think from a polymer physics perspective, the molecular response, macromolecular response to shear flow can be understood as follows. A typical shear flow can be created either by pumping fluid through a pipe. When you pump fluid through a pipe, there's no slip boundary condition at the surface, there's maximum velocity at the center, and that creates a parabolic velocity field. On the other hand, if you move the top plate, keep the bottom plate stationary, the momentum transfer in this case is going to be in z direction. And what you see is the velocity gradient is in z direction, flow direction is in x direction. So flow direction and velocity gradient are perpendicular to each other. It's a quintessential shear flow. By controlling this velocity and knowing this distance, we really control the shear rate. For that particular shear rate, if you measure the stress, the ratio of stress to shear rate gives you viscosity. Newtonian fluids have constant viscosity. Polymer solutions are shear thinning. Their viscosity decreases with increase in shear rate. The reason why it decreases is if you think about polymer coils exposed to this kind of shear flow, in such a shear flow, polymer coils get perturbed. And when they get perturbed, instead of being this sphere-like shape, they tend to become a little bit anisotropic and they can align with flow, making resistance to flow go down. When you stop the flow, entropically, polymers want to be in this state. So when you stop the flow, the elastic forces want to bring the polymer chains to entropically favored state. But it takes a finite amount of time that depends on the background viscosity. So this combination of elasticity and viscosity leads to a time scale relaxation time that we mentioned earlier. And in this context, we are going to call it a shear relaxation time. The shear relaxation time can be measured experimentally, and there are well developed theoretical models for understanding how you go from mildly perturbed coil to this unperturbed coil. And most of those theories rely on the idea that it's a time scale equivalent to the diffusion time scale of a polymer chain. Again, for details, you can refer to our papers as well as all sorts of textbooks describe this in greatest detail. All polymer textbooks describe this in greatest detail. What is described in less detail is, of course, the macromolecular response to extensional flow. And as I said, the extensional flows arise whenever you have these kind of liquid necks where the squeezing flow generates a velocity field where there is velocity gradient in direction of flow. Similar extensional flows will arise every time you have a contraction. So every time you have a contraction, you have porous media flow, you have flow from a large tube into a nozzle that would arise in every kind of 3D printing situation. Yes, there are extensional flow elements involved. And in extensional flow, because the velocity field or velocity gradients are in direction of flow, polymer coils can get stretched quite a bit. In fact, there's something called coil stress transition that can take place. And when coil stress transition takes place, you get a hydrodynamically an extended object, which provides much larger resistance to flow. The resistance to this extensional flow is called extensional viscosity. It's different from shear viscosity, except for Newtonian fluids, extensional viscosity is 3 times shear viscosity. So if you measure shear viscosity, you will know extensional viscosity because it's factor of 3 higher. In polymer solutions, though, extensional viscosity can be orders of magnitude higher. In fact, the extensional viscosity can be up to 1,000 to 10,000 times higher, which means that if you do the shear measurements, and a simple way of doing shear measurement is to take fluid between your finger and thumb and then move these finger and thumb backward and forward parallel to each other. So that simple shear will show you that the fluids are similar, maybe water-like. If you add small amount of polymer to water, they'll both appear water-like in shear. However, when you try to stretch the liquid bridge, or if you try to pump it through porous media, because of high extensional viscosity, the same fluid in extension start to behave like honey. If you try to do dripping, it will have a very delayed pinch-up. And this is something that really needs to be emphasized again. Polymer solutions can behave like honey in extension, even if they behave like water in shear. The hydrodynamically extended object, the stress chains, take, if you stop the flow, they again try to get to the unperturbed coil state, but it takes much longer time, especially in dilute solution, to get to this preferred state. And the time scale now is called extensional relaxation time. Unfortunately, the current state of art understanding of polymer physics does not really allow us to, if you look at textbooks, it does not really allow us to have a quantitative understanding of extensional rheology response, even if the shear rheology response is well known. And the theoretical models are still under works. And that has been a challenge for a very long time. So I'm going to mention this briefly, that even when we add cornstarch or we add basin or we add a small amount of flour to curries for thickening. What we are really doing, or what our grandmas usually do as a test, is a test similar to the test that I described. They often do tests where they will take fluid between finger and thumb and try to see if it's sticky enough, or you do this dripping test where you drip something from a ladle. It turns out that the extensional viscosity is also important in designing bread or making cakes, because as bubbles expand in bread, the flow field between the bubbles is extensional in nature. And for people who want to eat gluten-free bread, one of the problems is gluten is this long chain polymer, gives right extensional viscosity. If you don't have gluten, you have to add things like xanthan gum to really get the right texture and morphology for cakes and for bread and so on. Turns out that in most of the halwai shops, people do some version of this extensional test to figure out the viscosity or consistency of chashni. And I'm very fascinated by this, and I found a number of YouTube videos where regular people are able to show you difference between viscosity by doing this experiment again and again. And it turns out that's something that quantitatively uh, we scientists have been able to do only for the last 30 years. So the extensional shear viscosity measurements are routine. You can find rheometers almost in every university, major university, and in every industry. Extensional rheology characterization is not routine. The idea of extensional viscosity was introduced in 1906 by Troughton. Then in 1970s, there were some efforts made to really start measuring extensional viscosity for polymer solutions and melts. By 1990, there was this heroic effort made called M1 project. M1 refers to a polymer solution. The same material was shipped across to every different lab around the world, and then they were asked to make measurements of extensional viscosity with their individual methods. When they made measurements of shear rheology, everyone got the same answer. When they made measurement of extensional viscosity or elongational viscosity, for the same material, depending upon the technique, they got very different answers. So this depressed a lot of people, except it led to a lot of courageous research activity for another 15, 16 years. And in around 2006, um, it was realized that each experiment is showing the response of the fluid to a different extensional flow with different flow history, and each is correct. That does not really help us much, but it tells you that it's important to know what is the right measurement, and it's also important to control the deformation history. As it turns out, most of these fluids are very high viscosity fluids. M1 fluid was a very high viscosity fluid. When we think about sprayable paints or inks or sprayable insecticides and pesticides, the actual viscosity values are rather low and the extension rates are rather high, and most of these techniques can be used for those. In fact, in 2015, um, I summarized all the different techniques that can be used for a given shear viscosity, and here's a map of those different techniques. And when I was a postdoc at MIT, we tried to develop a jetting-based rheometer to get to these high rates and low viscosity fluids. As it turns out that when you have viscosity within 10 times water viscosity, it's easy to image this jet as it issues away from the nozzle. But if you increase viscosity or viscoelasticity, the jet flies to such long distances that the experiment becomes hard to control. So in 2013, Klassen had written this paper where he said, unfortunately, extensional flow is difficult to access experimentally, especially for solutions of polymers with a low viscosity or relaxation time. Really low viscosity systems that are used in inks and form the basis of formulation design in cosmetics and paints and so on. And that remained as a big challenge. In food context, Fisher and Windhab summarize it again around 2013. And I mentioned 2013 because that's around the time when I started my research group. And what Fisher and Windhab recognized was that approaches that aim to introduce extensional geometry are extremely useful to understand the material, but they're complicated by the fact that measuring devices are expensive. do not operate in the production time scale, and do not provide instrument readings easily be transferred to the process or to the baker at 4 o'clock in the morning. So when we started out, I had the goal of resolving all these issues and getting a way of making these measurements at high enough deformation rates for the right kind of polymer fluids. It turns out that there was already a commercial device that relied on emulating this stretching a liquid bridge between finger and thumb. And this commercial device is called Capillary Breakup Extensional Rheometer. It was commercialized by my postdoc advisor at MIT, Gareth McKinley, and it's based on ideas from Entov and collaborators who developed some initial ideas in 80s and early 90s. So here you see a comparison between water and PO solution. Even though there's only 200 ppm of PO added, it delays the pinch off considerably. Shear viscosity is only factor of 2 times. So if I took another Newtonian fluid which had viscosity 2 times water viscosity, that would have also pinched off or broken off at much shorter time scale. So it's clear that polymers produce some viscoelastic stress that delays the pinch off. And if we examine the neck thinning dynamics, it's well established now that we can learn about that viscoelastic response, and that viscoelastic response is based on extensional rheology. However, for Caber, you require around 50 milliseconds to stretch a liquid bridge. And even for water, even before the stretching is complete, the pinch off takes place. And so for low viscosity fluids, many of the actual inks that are used in every place from bioinks to photovoltaic inks to inks used in inkjet printer, those fluids lie in this regime that is inaccessible in Caber. So paint companies, cosmetic companies that I've talked to are all struggling with the same problem, that they acquired Caber, but they couldn't make measurements for many of their actual products. So when we started out, we wanted to analyze the material, measure the material properties that determine processability. To do that, we had to really understand how to design an instrument that could do this measurement. And our design is based on a deep understanding of fluid mechanics, self-similarity, and pinch of dynamics or pinching dynamics of complex fluids. I'll try to summarize these as quickly and smoothly as possible. And then what I'll show to you today is that there's a fair bit of polymer physics information that can be garnered once you understand the flow physics and you can do these experiments. The method that we created, we call it dripping onto substrate rheometry. And my claim is, it's a claim that you can verify easily today, this afternoon, this evening. My claim is that if you have a camera, even your cell phone camera, even if you're a theorist, you can replicate these experiments and have access to extensional rheometry from today. So what we do is we create a liquid bridge which looks similar to the liquid bridge that's found in Caber without using any moving parts. So we take a nozzle, place it at a fixed distance from a glass slide or a substrate, release a finite amount of fluid so that you get formation of this nice hourglass shape. The neck is thinner than the sessile drop and the pendant drop. The capillary stresses take over, they squeeze the neck, pushing the fluid out, and that neck thinning dynamics is governed by the same balance of forces that applies in Caber or stretch liquid bridge configuration or in jetting or in dripping. And by analyzing this neck thinning dynamics, we can make measurements of material properties that influence processability, extensional rheology response, and so on. So here's a list of papers that my group has published in last 5 years or so. And what has been really exciting for us is, we are able to make measurements right down to water-like viscosity, and that was what we showed in our first paper. But even though our first paper came out only 5 years ago, there are at least 25 different universities and industrial labs that are using this on a daily basis, and there are more papers in print with this technique from other groups than from our group even. And so what turned out to be an idea that originated in the fact that Caber, we could afford a Caber. It was around 50 to 70K $50 to $70,000 after the academic discount. So I did not have that kind of startup to get a cable, but I also knew that cable couldn't really do the measurements on that. That's a gap in understanding and in measurements that we really wanted to fill. So now the other companies, other industries and academic groups, even the groups that have their own cable devices, have adopted dosimetry. And the key aspect of dosimetry is enshrined in these four images. So for low viscosity fluids like water, the neck shape turns out to be this cone, and I also showed you a similar cone in the jetting. This cone formation is signature of what is known as inertio capillary thinning. So inertia and capillarity are playing a key role here. If you increase the viscosity, go from water to honey or glycerol, then the neck shape changes completely and it becomes a cylindrical neck. So these are both examples of Newtonian fluids. If I look at radius evolution with time, it decreases with t to the power 2 over 3. Here it decreases linearly with time. On the other hand, if I add a small amount of polymer, like the examples we considered before, then this viscoelastic fluid, if we just think in terms of viscosity, it still has low enough viscosity that it should behave like an inertia capillary response, but it tends to give you what is similar to a viscocapillary response, except even though the neck shape is similar to viscocapillary response, the radius evolution gives you an exponential decay. And so that exponential decay can be fitted to get a relaxation time. Lastly, many non-Newtonian fluids, many power law fluids, many formulations that have more than just polymer in them, they have other ingredients in them. These shear thinning systems tend to behave like power law fluids in terms of shear rheology, and also in radius evolution, they show power laws. But in terms of neck shape, you can see formation of these two cones. So there are very distinct time scales, very distinct pinching dynamics and topology. And Yelena and Naili went ahead, and this was early in the game. They went ahead and tried every fluid they could find in their kitchen and in their cosmetic cabinet. And you can see we have everything from printing ink to chocolate syrup and molasses that behave more or less like a viscous fluid. So you get cylindrical necks, whereas here is a list of polymer solutions which show you very nice, again, cylindrical necks, but the pinch-off dynamics has elastical thinning. There's also a comparison between egg yolk, which is viscous, and egg albumin, which is viscoelastic. And in the lower level, you see many of the commercial formulations where conditioner or mayonnaise or ketchup or hand cream tend to show a formation of these two cones. So if you want to go back and look at the actual fluid mechanics or force balance, there are four primary forces that are relevant here. Inertia, which is density times velocity squared. Velocity is the radius evolution, gives you r as a function of t, and this is just time derivative of that. Capillary stress is the stress that drives the flow. As the neck becomes thinner and thinner, capillary stresses go higher and higher. The viscous stresses, in this case, are these extensional stresses. So you have extension rate. The extension rate is given by r dot over r. So again, can be determined from the neck dimensions. And then if you have polymers present, there can be additional viscoelastic stresses that can be modeled using your favorite polymer model. So if you have just water, then we get an inertia capillary balance, and that gives this radius evolution of t to the power 2 over 3, and water just breaks rather quickly. But in case of polymers, there is a second regime that arises, and this second regime arises that gives you a balance between elastic and capillary stresses, and this elastic capillary balance results in an exponential decay. Here the data is plotted on a semi-log axis, and because it's plotted on a semi-log axis, the exponential decay appears linear. By fitting this linear regime, we can get a measurement of extensional relaxation time. In this particular case, the polymers term is defined by, say, an Aldrich B model, which is a fancy version of Maxwell model that I'd mentioned earlier. Right. So one of the first things we did was to make measurements for polymer solution. That's a dilute polymer solution. What that means is the number density of polymer coils is low enough that each polymer coil is far away from other polymer coil. So there's a concentration called overlap concentration, referred to here as C star. That's a concentration at which the number of coils is just enough that they start to touch each other or they start to overlap. At overlap concentration, the polymer solution viscosity is 2 times solvent viscosity. So, so all the polymers solutions that are shown here, except for 0.3%, have viscosity that's within 2 times water viscosity. So for these polymer solutions, if we try to make measurements on Caber, we get nothing. By the time liquid bridge is stretched, all the action is over, you're not able to make measurements of radius evolution. So commercial devices could not give us any measurement of extensional rheology or pinching dynamics. Here, what we see very nicely is if we plot radius evolution in a shifted time scale such that TC represents a time scale at which there's a transition from inertia capillary to elastic capillary, what you see is all these solutions, in spite of slight difference in their viscosity, because inertia capillary response only depends on surface tension and density, they approach asymptotically the same behavior. That's fantastic. And then in the elastic capillary regime, there's a concentration dependent increase in breakup time or filament lifespan, and the slope changes, meaning relaxation time changes. So here, all the breakup happens within 40 milliseconds. So it's a fraction of a second, but even this delay is something we need to control when we are trying to design fast printing processes, for example. Now, I mentioned that in Caber, we are not able to make this measurement because Caber really relies on using a laser sheet. And if your thinning and pinch off happen before the full extension is accomplished, which is true for all the dilute polymer solutions, you don't get anything. Furthermore, what happens in Caber is this initial regime is always missing. It's always missing because most of that transition happens while the liquid bridge is still being stressed. So a lot of theories that have been developed to understand what might happen that triggers formation of contribution of viscoelastic stresses can't be verified with Caber that easily. As the polymer coils get stressed in this extensional flow in the fluid neck, they can eventually reach a stage where they are almost stretched to the extreme limit. In this case, they resemble more or less a solution of rods in a fluid. And solution of rods in a fluid, again, have a Newtonian-like viscosity, but that viscosity is much higher than actual polymer solution viscosity, shear viscosity, and it's called the terminal extensional viscosity. And this final regime is called finite extensibility regime, justified on the basis that polymers can stretch only so much. So every now and then we are able to see this regime, but finite extensibility regime often falls below the length scale that can be resolved optically. So here is an example of data set that we get using dripping onto substrate. And what we highlight here is that as we vary the polymer concentration, we go from the actual solution viscosity is low enough that you can see inertia capillary to elastic capillary to finite extensibility transition. But when we go to higher polymer concentrations, the polymer solution viscosity becomes high enough that the initial regime is viscocapillary, followed by elastic capillary, and then a finite extensibility. If we analyze we can analyze many things from here, but the key thing that we really look for is the relaxation time extracted from elastic capillary regime. And what we find is elastic capillary regime gives you less than a millisecond time scale. This time scale is too short to be measured on even the more expensive Caber as well as the torsional rheometers. So these are some of the shortest time scales that can be measured. And there's a distinct transition from a slope of 0.65 to slope of 1. The concentration dependence changes above C star, more or less. So we wanted to explain why the relaxation times changes as we go higher and higher. Again, For some of you who come from polymer physics background, this is going to be a very elementary slide. For the rest of you, here is an adventure in polymer physics that you can have in few minutes. So whenever we take a polymer and put it in solution, there are three possibilities. Polymer hates the solvent, in which case the solvent is called poor solvent. Polymer coils bunch up into the smallest size possible. That means their number or mass is proportional to volume, or R is proportional to nk raised to power 1 over 3. Nk is number of effective monomers called Kuhn segments, and Bk is Kuhn segment length. So Bk is chosen to be large enough that you don't have to worry about the local chemistry effects. So it's larger than the monomer size, but it's small enough compared to the chain size. And Nk is less than the actual number of repeat units, and that is because you're trying to count the number of Kuhn segments, which is effective length scale. Kuhn segment size also is correlated with chain flexibility or local flexibility of chains. So regular flexible polymers like PEO have short Kuhn length of around a nanometer, whereas polysaccharides or cellulose-based materials can have Kuhn segment length, which is 20 times larger or more. If the polymer and solvent if polymer loves the solvent, then it swells, and that solvent is called a good solvent. In that case, the coil size is proportional to nk raised to power 0.588. And if we refer to this as mu is equal to 0.588, there's an intermediate stage where the interactions are just balanced right to give you n raised to power half dependence, or nu equals to half. And this is also something you can get from a random walk statistics. So people like this, especially when you're trying to model things. It turns out that when we increase the polymer concentration, go beyond the overlap concentration, because of presence of other polymer coils in close vicinity, the excluded volume interactions that lead to this expansion get screened, and in higher and higher concentration, eventually you start to approach this theta solvent behavior. So coil size changes as you change concentration of polymers, especially when you go above C star. If you have charges along the chain, then those charged polymers tend to stretch out, and their length scale is then directly proportional to number of Kuhn segments. Likewise, if you fully stress the chain, then the size is going to be R max, which is proportional to this. The ratio of R max to R naught or RF is called finite extensibility or extensibility parameter, and that depends on NK as well as nu, which could be 0.588 or half, depending upon you start with theta or good solvent. The ratio of R max to B is NK, or number of Kuhn segments, and that determines the global flexibility. For some rods, your flexibility is low, so this NK is going to be low. For flexible polymers like PEO, this NK is pretty large. All right, so what we're trying to understand is how this transition from 0.65 to 1 can be explained. And I just mentioned to you these different regimes. The single chain dynamics can be described in the following way. The single chain dynamics depends on two things: coil size, so this is R square described here, and the friction coefficient of the chain, or the drag coefficient of the chain. So again, we teach this to undergraduates in fluid mechanics class. We teach them something called a Stokes law. Stokes law allows us to calculate drag on a single sphere. What Rao said was that if we calculate drag on a single sphere or single segment, it's going to be viscosity times size of the segment. This comes directly from Stokes drag. And then we should multiply it with total number of those segments. So that's a Rao's scale. Zim later identified the fact that if you move one bead or one segment, it creates a velocity disturbance, and that creates a hydrodynamic interaction between segments. So the actual friction coefficient is not, for the entire chain, is not just this simple summation. What he instead used is the idea that the entire coil then behaves like a bead, So this is nk raised to power nu, which could be nk half into bk for a theta solvent multiplied with coil size. Experimentally, it was found that in shear rheology, dilute solutions behavior is Zim-like. In melts, it's Zauss-like. In semi-dilute solutions, which are intermediate, it seems that you need to account for local behavior using Zim theory, global behavior using Gauss theory. Now, again, details of this are relatively involved. So I'm going to skip some of these details and essentially mention this, that by using blob theory and a detailed understanding of polymer physics, we were able to show what leads to 0.65 and 1 concentration dependence. And my student Yelena, who was an overachiever, really went and verified that you do get slope of 1 for these many different molecular weights. What is more interesting, though, is the fact that if we have the radius evolution data, from that we can get capillary stress. We can also calculate extension rate. And by taking the ratio of stress to rate, we get an effective extensional viscosity. I mentioned for dilute solutions, the shear viscosity is less than 2 times water viscosity. So less than 2 times water viscosity is 2 millipascal second. Here, the extensional viscosity that's measured is orders of magnitude higher, right? So we really have this transition from, so here's the shear viscosity values, here are the extensional viscosity values. You're going from around 1 to anywhere between 10,000 to 100,000. Something that behaves like water in shear is behaving like honey in extension. If we take different molecular weight polymers all at C star, all these 3 different molecular weights will have the same shear viscosity, just 2 times water viscosity. However, the extensional viscosity is orders of magnitude apart. And this tells you how changing molecular weight can really influence your raw formation dynamics, dispensing behavior, and so on. But the key takeaway from all my presentation is material characterization in shear flow is not sufficient, especially for dispensing applications. It's important to characterize the extensional response. We've spent a fair bit of time trying to understand ins and outs of how to better understand the effect of polymer concentration, molecular weight, and so on. And then the critical question that arises is what happens if you go away from PEO and you look at some of the other polymers that are used as rheology modifiers. So one class of materials that's used quite a bit is polysaccharides or cellulose derivatives. And these are usually sourced from plants and are water soluble, and they're also typically biodegradable. So there's a lot of push to use this. Many of these are safe to eat, so they form essential ingredients in foods. And here's a list of some of the most common ones. So CMC, you can find carboxymethyl cellulose in everything from construction to food stuff to your toothpaste to denture adhesives to baked goods to beverages. Sometimes you make smoothies or mango shakes appear more pulpy by just adding polymer to them. They can create that kind of mouthfeel. Same for HPMC, HPC, HEC, hydroxyethyl cellulose. We're going to spend a fair bit of discussion on that in the coming few slides. And what you want to understand is it doesn't matter whether you're eating your ice cream that's made commercially or using your toothpaste or shaving cream. If you use Gillette, it has both HEC and PEO in it. That allows you to get the right kind of foam and so on. So what my student decided to do was to take PEO and HEC as 2 quintessential examples of polymers. She picked molecular weights that are comparable, but the Kuhn segment of HEC polysaccharide is much longer, 20 times this. The number of Kuhn segments is much larger in PEO, which is also the case because this is small, so this has to be large. And this shows that this is fairly flexible and will be more extensible than HEC. But if you calculate the coil size comes out to be the same. If the coil size is the same, that means properties that depend on coil size, like the actual coil size as well as the relaxation time, shear relaxation time are going to be similar. And that's something that we just mentioned a few minutes ago. So if R square is the same and this formula also uses R is the same, so it's going to be eta s R cube is the same, then relaxation time is the same. So if we make shear rheology measurements, what we find is below the C star or overlap concentration, which turns out to be the same for these because coil size is the same, the behavior is indeed matched. So this gives you an example of how chemistry independent universality exists for polymer solutions. They give you the same response as long as the coil size is similar in dilute solution. Above C star, above overlap concentration, HEC can go to entangled state more quickly, and so it has a stronger slope. But let's just focus on dilute solution. So based on this dilute solution, we have similar viscosity, and an estimate of Zim relaxation time is also the same. Now we want to figure out what happens if we take this system, and here I'm showing you an example where they have same actual concentration, same measured shear viscosity, the estimated relaxation time is the same, and they are in water, so their surface tension is the same. However, the pinching dynamics is very, very different. PEO has this delayed pinch off, HEC does not. So you can't explain these differences based on just shear viscosity or relaxation time or surface tension effects. And to explain this, we really had to go back and dig through understanding of coil stress transition and so on. So I'm going to skip through some of this. And the key idea that comes out of all of this is that we were able to quantitatively come up with a criteria that tells you why we see such a sharp transition in the radius evolution for PEO. It undergoes what is known as a coil stress transition. And the criteria for coil stress transition depends on the friction coefficient for fully stretched chain compared to friction coefficient for a coil. And for something like PEO, which can stretch quite a bit, this number is large enough that we see a very pronounced elastic Capillary regime. Some of this was published only recently, and you can avail of those in these macromolecules papers that just came out. So jumping ahead to comparison of relaxation time versus concentration, we were able to not only look at the slopes, how they change when you go above C star for HEC versus PEO and how that depends on the chemistry. What Yelena, my student, was also able to do was to get to the low enough concentration where the behavior becomes concentration independent. And we also wrote down the criteria for a minimum concentration below which elastic effects cannot be measured. And all this is a nice story, but what I hope I showed you so far is we made contributions that allow us to make actual measurements of extensional rheology and pinching dynamics of almost all commercial industrially relevant formulations, biologically relevant materials, and we call this technique DOS geometry. And one of the key aspects of this technique is it's frugal. It can be used by almost anyone who has access to a camera. For low viscosity fluids, you do need a high-speed camera. For high viscosity fluids like honey or ketchup, you could do experiments right with your cell phone camera. We've gone through a very detailed analysis of chemistry dependence, concentration dependence, molecular weight dependence of extensional properties. And the experimental data is unique and is already motivating other people to think about related problems. And now I'm just going to give you very fast summary of some formulations, how they differ and how their differences are manifested more in extension than in shear. So if we think about Pantene shampoo plus conditioner, and just the conditioner, they are more or less similar in the soap that they use, sodium laureth, but they might have different other ingredients. In case of shampoo plus conditioner, there's guar gum added. In case of shampoo, there's hydroxypropyl methylcellulose added. And in case of Conditioner, they usually have lipids and other things that modify the behavior. But it turns out that their shear rheology is designed to be quite similar, especially in these high shear rate regimes. And that means that in a bottle filling plant, you can use more or less the same parameters to fill bottles. Even then, they sometimes face problems because the elasticity in these is different. And again, it's same Pantene, but shampoo, two-in-one, and conditioner. A standard way of looking at elasticity is to do an oscillatory shear measurement. If you know much about these, you'll know that this is showing you quintessential viscoelastic liquid response, where G prime has slope of 2 and G prime has slope of 1. And these are relatively nicely matched for shampoo and two-in-one. Conditioner actually behaves more or less like a gel, so it has a constant frequency independent G prime and G double prime. So there's definite difference between conditioner and two-in-one based on G prime and G double prime, but the actual shear viscosity plot didn't show you much difference. However, when we use dripping onto substrate analysis, we find they show very different pinching dynamics, and the material properties that govern their pinching dynamics are very distinct. And so this is one way to really distinguish between different formulations as to how they're going to behave, and we can fit the radius evolution and so on and so forth. The last example I'll give you is of cellulose gum that's used in food rheology. And here we are looking at cellulose gum in a glycerol water mixture. And cellulose gum is a charged polymer, so it shows some sensitivity. The shear rheology shows a lot of sensitivity to amount of salt. And again, to understand this, it's a charged polymer. In absence of salt, chains are stretched out. So you get coil overlap to happen at much lower concentration. But as you add salt, some of those charge interactions get screened, coils become smaller and smaller. So on adding salt, the overlap concentration, which is where this specific viscosity is 1, shifts to a higher value, and the overall viscosity also goes down. So shear viscosity gets affected quite a bit when you add even 0.005 molar of NaCl. Right? So this is something that's very important. Every time you're trying to make food formulations, we do add a certain amount of salt. And depending upon how much salt you like, your curry might turn out to be thinner or thicker just because of the thickener being a polyelectrolyte. So we carried out experiments to measure the actual neck thinning dynamics, and it involves a fair bit of detail, but the summary from the extensional rheology characterization was that because the extensional properties depend on stress chains, and the stress chain size does not change when you add salt, we got more or less the same response in extensional rheology with and without salt. And this is again something that's important if you're trying to think about designing things as dipping sauces or even dispensing fluids. My student Naili did a very detailed survey of studies of polyelectrolytes in terms of shear and extensional rheology, how salt affects those, how choice of polymer affects those, how choice of solvent affects those. And even though a lot of shear rheology was available for charged polymers, she mapped out a range of a very grand range of properties in terms of extensional, and some of these papers are in progress. But again, what I would leave you with is the idea that DOS geometry is pretty versatile. It allows us to look at formulation design, also investigate basic polymer physics questions, and in the end, I hope at least some of you would be motivated to start using some of the both concepts that we discussed today and maybe DOS geometry, especially if you're interested in designing your formulations for 3D printing, for fiber spinning, for determining spinability, or for designing formulations used in food, cosmetic, pharma industry. With that, I'd like to end my talk and I'll be very happy to take your questions. My email address is fairly simple. You can find it on the website. It's viveks at uic.edu. Feel free to send me an email. Feel free to find me on LinkedIn. Feel free to visit our website and give us comments. And I'll be very happy um, to address your questions right now. Thank you.
Hello.
Yep.
Uh, so we have received some queries from our participants. Let's take them one by one. Uh, Somebody wants to know few additive manufacturing companies in India.
Mm-hmm.
I'm not sure how much it is relevant with this talk, but a person has floated a question. He wants to know
Mm-hmm.
any additive manufacturing company in India.
So well, there are definitely additive manufacturing efforts in India, and from the big companies almost, well, I'm not aware of, I don't interact with companies in India directly to know who's investing to what extent in additive manufacturing in India. But I think the global effort, even it doesn't matter whether it's construction or it's creation of beautiful cakes, three-dimensional cakes using chocolate or other products. For all of those, now they're additive manufacturing efforts. And then, of course, there's the additive manufacturing in context of, say, photovoltaic, and even some of the American companies like Konarka, that trying to make solar cells. The Konarka, the name should give you the hint, was a company that was also established by some Indian scientists and entrepreneurs. But I haven't followed the additive manufacturing progress in India, at least in the commercial space.
All right. Oh, they can also Google this thing. It is not very difficult to find out what are the companies leaders.
Mhm.
Uh, there is one more question. As rapid prototyping or solid freeform fabrication has been growingly rapidly increasing, so what should be processed of joining metals to make objects from three-dimensional model data? Are you getting this point?
Yeah. So again, this is a little bit orthogonal to things that we were discussing today. But if we think about so I can take a step back. There are there are few different ways in which people are using additive manufacturing of metals. When I was at MIT, I was involved in some of these discussions with the prominent group, Ellie Sachs group, who were actually pioneers in making 3D printers back in 90s. And I also talked to companies that were trying to print molten metals to make devices or electronic circuits. And when you think about just printing metals, most of the metals are Newtonian fluids. The more challenges arise from control over temperature. Now, there's a second set of printing methods that involve printing into metal powders, um, or using laser sintering, and there's a whole spectrum of effort being made in India and here. I sort of stay in the domain of soft matter as much as possible and only look at metal based printing out of curiosity every now and then.
Right. There is one more question.
Mhm.
Newtonian fluid has no
Mhm.
memory.
Yeah.
He wants to know why.
Um, well, if you wanted to be really picky about it, what you could say is it has a memory that's relatively short. It's so short that it does not really matter to us on a real time scale of processing. Because what you have to remember is Maxwell, and you can find Maxwell's paper where he gives this initial idea of taking a Hookean spring and a Newtonian dashpot in series. That particular idea was for invoked was for air. So air is Newtonian fluid, but Maxwell recognized that under some conditions it can have some elastic effects. Except the relaxation time that you find for air or water is so short that on any realistic processing time scale, you can effectively say it relaxes instantaneously.
Right, thank you. There is one more question.
Mhm.
Uh, is there any effect of shear thinning in various grades of lubricant used in industry?
That's a very good question. So of course there is some effort made to control the amount of shear thinning you have in lubricants, and we interact quite a bit with Lubrizol. I've not included any of the discussions that we've had with Lubrizol here or um, other companies, but so there are two or three things that are important for lubricants. One, in context of lubricants, the deformation rates are very high. So deformation rates can approach 10 to the power 5, 10 to the power 6, and you can't make those kinds of measurements. Those shear rates can't be accessed on normal rheometers or normal geometries. That's one. Two, so if you have any shear thinning at those rates, people typically don't measure it. The person who could measure it very nicely was Scott Blair in Georgia Tech, who had a special device built for this purpose. Um, so shear thinning can play some role. Now, in lubricants, what you really want to figure out is the normal force that's generated when you have fast-moving surfaces, and so there's some research work that we hope to do and find some connections even with our extensional viscosity measurements. Because if you really think about extensional viscosity, it's something that's based on the normal force component because it's the stretching force in direction of flow. So it's more correlated with the normal force component, except the flow field is slightly different. So shear thinning plays important role. Shear thinning happens at rates, or the rates that are realized in lubricants are too high for most inertial rheometers to allow you to make those measurements. So those are the 2 points that I think you want to take away for lubricants.
There's one more question. How can we reduce the surface energy of rough surface without polishing it? Please suggest the method for metallic substrate, how we can reduce surface energy of textured surface.
So if you're trying to reduce, well, metals always have a very high surface energy, and texturing can get you some benefit because of sort of you get into a Cassie-Baxter kind of state, which means you have the roughness comes into play, and you are at an intermediate stage between the actual solid and air, right? So the only way you can get away from the metal surface energy and get additional benefit is by either using some kind of coating, and if you don't want coating of an organic compound, which can obviously reduce the surface energy considerably, sometimes what you can do is use processes like atomic layer deposition, where you can get a very thin layer of another inorganic oxide maybe that will have slightly lower surface energy and might also get some benefit of changing roughness, initial roughness.
There is one more question. How to categorize
Hmm.
lubricant oils on basis of shear thinning?
How do you characterize what?
How to categorize lubricant oils?
lubricant uh,
Yes,
dyes.
oils that we use in machining, the oils.
Um, well, again, as I said, I'm not sure how much real data is released to public about the actual viscosity that's relevant in the real lubrication flow or flows that lubricants account. But if you had access to the shear thinning data, then you can extrapolate to higher rates. And the way to actually look at degree of shear thinning is to fit the viscosity versus shear rate plots with simplest model is power law. That's sometimes not effective. And a little more involved models would be cross model, Crow model, Crow-Yasuda model. Each one comes with additional parameters, and if you have more specific questions about it, send me a detailed question, and we'll be happy to discuss.
There is a question on the difference between viscosity and extensional viscosity.
Yeah. So difference between viscosity and extensional viscosity is something that, again, if I pump fluid through a pipe and I look at the Hagen-Poiseuille flow, which is what we cover in most of our classroom teaching, then if you are far away from entrance, far away from exit, it's a fully developed flow, then you'll get a very nice parabolic profile. And that parabolic profile is a good example of shear flow if you are looking at a flow through a pipe. In that case, the resistance is controlled by shear viscosity. Other way of thinking of shear viscosity is if I place fluid between two plates and I keep one plate stationary and move the top plate. In that case, I have momentum transfer from the top plate towards the stationary plate, and the degree of momentum, the momentum transfer is controlled by shear viscosity. So that's shear viscosity. So shear viscosity is what would be most typically mentioned when people are thinking about processing, because flow through a tube depends on shear viscosity. However, extensional viscosity is something that is going to arise when you have sort of, if you go from a thicker, if you think about flow in a syringe, so when you go from a tube of a syringe into the nozzle of a syringe, because if you push at the fluid at a constant rate, if your flow rate is constant, then as you go from larger area to smaller area, the velocity has to go up to maintain the flow rate. So, so if you have something like a polymer chain, part of it is going to be in the low velocity region, part of it is going to be in high velocity region. The example that I give sometimes is that you can imagine a little kid who is holding hands of two people. One walks really fast, one walks really slow. So that's what an extensional flow can do. Eventually, the kid is going to get, hopefully, not stressed too much to be harmed, but will get stressed. The same thing happens for polymer chains. They get stressed. So extensional flow or extensional viscosity is resistance to a flow field where velocity gradient, variation in velocity, happens in direction of flow. And this can be induced in converging channels. This can be induced in porous media where you have converging, diverging channels. And as I said today, it can be induced in liquid necks during drop formation, whether it's in spraying, jetting, or dispensing.
Uh, there are a couple of more questions.
Sure.
What is the future scope of polymer composite manufacturing by FSP processing?
By FSP.
FSP. FSP, I'm not sure what is this FSP process.
Well, I think the good answer to a question like that is future is always bright, and you have to hope that future is bright. And of course, the future of composites is bright because, irrespective of how we think about the material technologies that are being developed, um, one of the key aspects is we always want to make composites because it allows you to combine materials and get synergistically better properties than individual materials themselves. And with polymers and some combination of reinforcing fibers, you can always reduce the amount of weight and material cost involved in things like transportation, which is why eventually you would find that things like cars and trains and planes, everything gets to be lighter and more polymer composite based rather than metal based.
Okay. And there is one question, how viscosity influences dripping onto substrate?
So I think the answer can be oh, given more simply by just going back to this one. Right. So if you look at this image, if I have low viscosity fluid like water, the pinch off happens within a with in a very very short time. So it could be few milliseconds. As you increase the viscosity, the neck thinning becomes slower and slower. And so if I increase the viscosity to maybe 100 times water viscosity, both the neck shape changes in that you can visualize in dripping onto substrate. The neck radius now decreases linearly with time instead of t to the power 2/3. Actual viscosity starts to play a role for viscocapillary thinning, plays no role for inertia capillary thinning. So for water and ethanol, there will be some difference because the surface tension are different, but and that changes the driving force for thinning. But viscosity will not be the reason for difference between pinch-off dynamics of water and ethanol. However, between water and glycerol or water and honey, the difference is stark because one is going to give you inertia capillary, the other one is going to give you viscocapillary. For glycerol, honey, molasses, or glycerol water combinations, you can actually measure, if you know the surface tension, you can map out the viscosity, or you can measure the viscosity, shear viscosity even. Because for Newtonian fluids, the extensional viscosity is just 3 times shear viscosity. The bigger difference arises in the viscoelastic or power law fluids, where viscosity is not the only, shear viscosity is not the only thing that affects things, is the actual extensional viscosity, and all of that is correlated with what happens to the microstructure. For polymer coils, they can get stressed. For foams, these bubbles can slide across each other. For some other yield stress fluids, the microstructure actually breaks down, and that's why you get some kind of a rupture like behavior. So I hope if you want more details, these are discussed very nicely in a review by Gareth McKinley in 2005, or they're discussed in most of the papers that we've put out.
Thank you so much for this illustrative answer. There's one last question that we have received from the chat box.
Mm-hmm.
What is the effect of nanoparticles on geometric properties?
Ah, okay, so we'll need another 2 hours to discuss that, but I'm going to give you the bird's eye view. So the simplest, smallest effect, if you have low enough concentration of particles, was discussed by a good friend Albert Einstein in 1905, where he basically said that the viscosity increases in proportional to volume fraction. When you go to higher and higher concentrations, then we see both shear thinning and shear thickening behavior with high concentration particle dispersions. When you start to go to high enough particle concentrations, you can have jammed states, and so that means the viscosity goes up quite a bit as you increase particle concentration. We are indeed looking at the rheology of particle suspensions because our funding comes from PPG, they make coatings, and coatings or paints are full of particles. So I did not show you any of our results on particle-based systems, but but that's something that we are thinking about more and more. And there, the big unsolved problem is almost all the effort and theory and understanding is for systems where particles are dispersed in a Newtonian fluid. In paints and in real systems, particles are dispersed in a Newtonian fluid, but there's also polymer present in that background solvent. So the background solvent is viscoelastic, and and that is not as well understood. And that's where we are really making an effort. These are all very good uh, questions, and unfortunately, we are not in the same location. I would have otherwise sat down with some of you, and you would have enjoyed discussing this over tea or samosa or something, a nice lunch. Or and I hope that would happen at some point in future, and we'll get to individually meet many of you and see you in conferences and so on, and wish you luck in your own individual research enterprises.
Thank you so much, sir. We are also hoping for the same. And now I guess that there are no more questions. So in the end, I would like to extend my thanks for outstanding and stimulating talk, wherein you talked about the research aspects related to formulations and processing, rheological and surface engineering of different engineering materials. And I must admit that it was done in a very illustrative and lucid manner. Well, eventually, on behalf of all the organizing team, I would like to once again thank you from the core of my heart for accepting our invitation as one of our speakers, and especially taking the pain of speaking during the late night hours as per the US time. We are highly indebted for this act of kindness, and we certainly hope to have similar such interactions in near future, and maybe physical interaction this time.
Mm.
So thank you so much for connecting with us.
Yeah, no, this has been a fascinating adventure, and I really look forward to more such opportunities and
Right,
opportunities in person too.
right, sir, right. That is more a lively interaction.
Yeah, yeah.
Yeah. So anyway, thank you so much for connecting.
Okay, thank you. Bye, everyone.
Bye,
Enjoy
bye.
your afternoon. It's 2:30 a.m. for me, so I'm going to go off and um,
Right. Thank you so much once again.
yeah. Bye.
Bye. Yes, sir. So, dear participants, we will again rejoin for our next session at 2:30. Thank you so much. Thanks for connecting. Very good afternoon, dear participants. Welcome back to the second session of the second day of the STC on contemporary material technologies. We are joined by Professor Apur Kumar Sharma. It is indeed our pleasure to have with us Professor Apur Kumar Sharma. He is professor in the Mechanical and Industrial Engineering Department and coordinator of Design Innovation Center at Indian Institute of Technology, Roorkee. He completed his MTech in SIM and PhD in Surface Engineering from IIT Madras. His areas of research include advanced manufacturing methods, hybrid processing, hybrid processes. His areas of research include advanced manufacturing methods, hybrid processes, microwave material processing, in particular microwave drilling, microwave casting, microwave joining, and microwave cladding. He has guided 14 PhD theses and 7 are in progress. He has published more than 100 research papers in renowned international journals and more than 100 in international conferences. He holds highest citations among Indian researchers with a whopping 2619 citations. Dr. Sharma is also a reviewer of 38 reputed international journals. Dr. Sharma has been awarded 4 patents and 9 are in progress. He has completed 8 funded research projects, including SPARC, DST, Indo-Ukraine, Indo-US projects. He is a fellow of Institute of Engineers, member of Hydraulic and Pneumatics Committee, Bureau of Indian Standards. He has been awarded DARD Fellowship to work in Germany. He has NPTEL video course on advanced manufacturing processes. I now take immense pleasure in inviting our distinguished speaker, Professor Apurva Kumar Sharma. Please start with his presentation. Now hand over it to Professor Sharma.
Yeah, thank you. Thank you, Dr. Rajiv. Hello, Dr. Rajiv. Am I audible?
Yes, sir, you're audible. Please go on.
Yeah. Just is my screen visible?
Yeah, visible, sir. So kindly put it
Yeah.
on presentation mode.
Yeah, I will put it. I will put it. So thank you so much. Thank you, Dr. Rajiv, and thank you, NIT Jalandhar, my colleagues over there, who have shown immense love towards me, inviting for this particular session, and giving this opportunity to interact with all of you. I can see around 50 participants have logged in, and I believe all these participants are like not from NIT Jalandhar, so it might be spread out from different corners of the country. Am I correct, Dr. Rajiv?
Yes, sir. They are from different parts of the country, also from southern part of our country.
Okay, that's fine.
Yes.
That's good.
Yes.
So next maybe 1.5 hours, I'll try to talk to you. I don't say I'm delivering a lecture, but I'll try to talk to you. Had it been a physical mode, it would have been more interactive. But now that interaction is possible, but a little limited. Okay, but still, at any point of time, people can stop me, or we can have some kind of discussion in between also, if you need so.
Yes, sir. We have instructed them to
Mute.
to mute the mic and put their queries at the end of the session. They will be giving
Okay.
us the queries, and if you want, we can ask them to unmute the mic if they want to ask anything.
No problem, no problem. So not necessary. So whatever you are following, I will go with that. No problem for me. Fine.
Right.
So maybe at the end of the session, we will have some kind of question answer session, right?
Sure, sure.
And yeah, yeah. So I'm going to talk on a kind of like very unconventional topic, that is material genomics. I don't know, many people might have been aware about this material genomics. At least all of you might be aware about human genomics. So at the very beginning itself, let me be clear about this fact that I'm neither an expert in human genomics nor an expert in material genomics. But I have dared to bring this word into this forum just to create a kind of like awareness, so that other people who uh, who who wish to be an expert, or who wish to carry forward their research in this direction, who wish to get benefited by this type of information, will be benefited. But I'll just give a kind of introduction to this, and then I'll try to link with my own area of research. And as I could come to know the time of when we were talking about finalizing the topic, etc. So I was like told that it will be more interesting if I talk about one of my processes. So as Dr. Rajiv said, like I have been working in this field of microwave material processing for quite some time, and in the process we have developed a few technologies, and today I'll try to discuss one of those technologies, maybe little okay in details, and then we'll try to have a kind of discussion. Okay, so that there will be like two parts in this discussion. One will be on material genomics and how one can get benefited with this material genomics, and then keeping this material genomics in our background, like how we can see material processing or the challenges in material processing in the same way the people are trying to see the material genomics. So there are two parts, like two distinct portions in this. One will be devoted on the material processing, the other one is material genomics. We'll see how we can get a kind of link. And of course, without being an expert of this, just we'll have a, I'm also learning along with you, so we'll have a kind of okay learning experience on this. So as requested by Dr. Rajiv, I am going to the full screen mode, presentation mode. Am I visible? Like my presentation is visible, Dr. Rajiv? Is it
Yeah,
okay?
sir. Yeah, sir. Yes.
Okay, so I am
And
trying to follow your instruction.
no, no, sir. Please don't embarrass me.
That's fine. That's fine. Okay, so sometimes if that mic is not working or something like that, you can give me a ring or something like that. Okay.
Sure, sure, sir. Sure.
The morning I was taking a class, then somebody called me that I'm not able to listen. So it's a kind of basically internet issue, and at the same time, maybe 80% of the students they were listening, but only 20% they had some issues while listening to me. Okay, no
Yeah, it
problem.
happens.
So let's move. Let's move.
Yeah.
So as I said, like genomics, like I want to bring in. So for that material before going to material genomics. So human genomics, what is human genomics? But very quick look at the human genomics because it all started with that, and then a very brief look at the material genomics, and then some thoughts about the material processing, because I work in material processing, so I should talk more on material processing. Then specifically a process that is microwave drilling. Okay. Coming to human genomics, so this is one of the most impactful researches the world have ever seen. So all of you might be knowing that Human Genome Project, this was one of the most expensive, most elaborate project, and it was spanning around 13 years, started in 1990 and ended in 2003, and it as much as 3 billion, something around, okay, 3 billion DNAs, okay, were sequenced during this period. Okay, 3 billion DNA pairs. So that you can think about the quantum of like work that it was involving. Okay, and the rigor of the project, the involvement of human involvement in this project, the capital investment in this project or capital involvement in this project. So this is undoubtedly one of the largest projects. So that is called the single largest undertaking in the history of biological science. And It was an international public project. So it was led by United States and a complementary private program as a complementary private program. And it is a signature scientific achievement, people call it. Yes, 3 billion DNA pairs were sequenced in this project. So one can easily understand. This gentleman, Francis Collins, he was heading this project. Okay. And the goal was uh, to determine the base pairs that make up human DNA and to identify and map all the genes of the human genome from both a physical and a functional standpoint. As all of us we know, like DNA, this is the DNA structure, okay, DNA structure, and in that genes are there, so those are to be mapped. And the key findings are there are approximately 22,300 protein coding genes in human beings, the same range as in other mammals. Human genome has significantly more segmental duplications. So this was another finding. And then fewer than 7% of the protein families appear to be vertebrate specific. So this was published in 2003. As I said, it was started in 1990 and then 2003. It's most of its uh, findings were made public. So what are the things involved in this? So undoubtedly, like technology, labor, and so many other things were involved in this. Expenditure was like unimaginable. I'll give you that estimate also to some extent. Okay, and then it impacted so many so many areas like building technology, supplies, labor, means almost each and every aspect of a society was being touched. So if you see the functional impacts, so this right hand side, these are some of the areas where it had the impact. So people now in a better position how to design a medicine. Okay, people are now in a better position how to design food. Okay, so all these things, say agriculture field also. So agriculture field also, if we want to design a particular crop, a particular seed that will suit a particular type of human being. So for that we need the human genome data. Okay. Similarly, the biotechnology, industrial biotechnology, then scientific knowledge, of course, now we are richer by manyfold. Okay, what we didn't know few years back, now we know much more than that. So its impact is really very high. So fields of like application, if you see human health, now you can design a drug to suit a particular human being, particular person. Okay, so that is how that precisely one can now go for. So now targeted, now many of you might be knowing like targeted delivery of like drugs. Excuse me, just I'll take one. Sorry, this was a kind of urgent call. Okay.
It's okay.
Yeah. So now, like it is not only human, but also veterinary industry, biotech industry, and almost all, like including environment. So all aspects of a society or of our society got impacted by this human genome project. Okay, and this might have influenced, okay, the policymakers or the scientists. Yes, if human genome project could give us this much of impact, okay, why not we think in other way. So this is where we stand, like human genome sequencing project. So impact is direct impact in employment, in as far as the employment is concerned. you can see. So this is in billions as far as 2010 data, $1 billion. Okay, so it impacted what is that? 38 lakhs 27,495 billion dollars. That was the impact, as far as employment is concerned. Similarly, personal income output, then state and other tax, etc. And if you talk about US tax revenue, okay, they were okay richer by approximately $50 billion. So this is what the impact of the project was. Okay, so it is huge, and like even if we do not talk about the monetary terms, the scientific impact was immense, and the knowledge the human being could gain out of this project is enormous or never before. So therefore, this might have influenced another project, okay, specifically the US people to take up another project that is called Material Genome Project. That was Human Genome Project, and this is Material Genome Project. And okay, maybe many of us may not feel good to accept that in many cases US is leading in terms of scientific development or scientific research, technological development, and so on. So here also, in this case also, it is like no strange that US took the lead. And the reason may be, as I said, like Human Genome Project, so which had an impact of several lakhs of $1 billion, okay, as far as the economy is concerned. So US economy was impacted like that, and the benefit was not restricted to only US, so it got extended to other countries also. If the human data or genome data are available, then why not other countries can also use for their own purposes? Okay, so of course those like international treaty or agreement and all those things, those things have to be done. So that is like that is always done in political or diplomatic level. So all those things, mechanisms are there. And one more thing is Human Genome Project was like it was not completely government project. It was like a public project as well. Like some private funding was also there, and some other firms from outside the country, from outside US. Okay, they also participated in that, and obviously they were direct beneficiaries of the outcome. So similarly, if like some scientific outcome has been there, then that is for the mankind. Okay, now that might have like influenced the other scientists, and then they went for Material Genome Project. So what is Material Genome Project, and what is the importance why we should go for that? So to know that, so probably one thing we must appreciate or we must understand that there are discoveries. As far as materials are concerned, material discoveries are also there. As we know, like we have traveled this far, right from Stone Age. What is stone? Stone is nothing but a material. Then we came to Iron Age. What is iron? Iron is nothing but a material. Bronze Age. What is bronze? Bronze is a material, another material. Then slowly we came like that. Then probably we entered into silicon age. Okay, and now we don't know towards what we are moving at the present. Now all these things like developments are taking place. Like materials are being discovered, they are being developed. So iron, whatever the form iron was used in the Iron Age. Today we use iron, but not in the same stage. We got a different variants of iron now, or we have modified iron, or we have used iron to such a great extent that sometimes we forget that this is also iron. Okay, we have so many varieties of steel that we do, sometimes we forget that steel is also basically iron. So like that, it passes through enormous development after discovery for any material for that matter, and this is a kind of continuum. So it is happening. It is happening. Then we go for property optimization, like say iron, it gets rusted. Okay, so it is of less use in certain applications. Now we have got stainless steel, which is free from rusting. Similarly, it is, I'm giving you one simple example, which a mechanical engineer probably is very much like aware of. But the same is the case for like other like chemical materials, chemicals used in like chemical engineering, chemistry, and other things. And same is the case for like optics, optical materials. Silica. What is silica? What is silica? Silica means glass, SiO2. So today is also there, like silica we are using, and it is there from the beginning of the earth that it got formed. The silica was there. Sand. Silica is nothing but sand. But the same sand, what is there in the earth, and the same sand, okay, probably we are using for our specs, okay, for all other sophisticated purposes, for the costly lenses, okay, they are not in the same category. Maybe the chemical equation is same or chemical formula is same, SiO2, but we have optimized its property to a great level, and we have changed its functionality, okay, to suit our requirement. So slowly, so these type of things like materials are there, and we have developed them. Then we have optimized their composition or whatever, like to suit our properties, to give appropriate functionality. And then we have started designing material also. What is that? We are designing alloys. Today so many alloys are there, which are like very new. Every day there are new alloys, or new materials, new composites are coming up. So these composites, so they are probably they are not existing in the same fashion as we are using it today. So these composites are being designed, developed, integrated. Okay. So my this laptop, this casing is of different material, my screen is of different material. So behind the screen, the LCDs are of different material. Okay. But if we go back, so origin or the root of these materials will be some known material only. But we are designing it in a different way to get different functionalities. Similarly, so once we design something, we need certification also. Okay, so that yes, I can be sure of, yes, this has got this like functionality, and this will be harmful or it will not be harmful, or this should be used in this kind of environments. This has like these type of effects and so on. And that is until and unless some authority says that, it is difficult for me to understand or difficult for me to accept that yes, this has got this kind of properties or something like that. Okay. Then manufacturing. So probably I will be emphasizing most of the part of my talk on this manufacturing part. So materials once developed, now it has to be reshaped. It has to be worked upon. It has to be like given a kind of shape or functionality. Okay. So for that we need to manufacture them, process them. Okay. Then only so it will go for deployment or some like somewhere in the application, be it aerospace, be it in shipbuilding, be it in motor vehicle building, be it in like laptop manufacturing or whatsoever. Okay. So a deployment can be of like anywhere. Like say polymers, we are using polymers for various purposes. Even polymers we are using for like our manufacturing shoes. Okay, where probably like 50 years back or 70 years back, people were never thinking about that. Yes, one day we will have, or we will have to wear um, uh, some shoes other than leather also. But today, that is the order of the day. So deployment is there in that also. So it's like deployment is like in different fields, and so for those targeted deployment, we may have to design our like material in a different way, or in an innovative way, okay, so that the particular functionality can be mm, imparted, or can be embedded into that material. So that needs tremendous data, that needs tremendous scientific knowledge. So how to do that, how to go about that. So this is the challenge. So challenge is we need deployment, okay, we need deployment at various these things, mm, spheres of our life, okay. Materials are being developed, okay, our everyday materials are being developed, and it is going to be deployed. But what is the time gap between them? Material is being developed and it is going to be developed, deployed. What is the time gap between them? Then my application, it may be other way around also, my application needs this type of material, now develop it. So what is the time that will be required? Now everybody in this world is crying for one vaccine. If somebody gives tomorrow one vaccine, so probably he will be treated like a god. Vaccine for this, I'm talking about coronavirus, coronavirus. Okay, and what is that? As I said yesterday, also I said it is a material. So now we know the deployment, but we don't know the material. And even if we know the material, we are not in a position to deploy it because of this certification. Because of this certification, so it needs to be authenticated. It needs to be verified. It needs to be authenticated by the appropriate authority. Then only we can go for like deployment. So therefore, there is a huge time span. So last year, as you know, like in December or so, this first corona cases were detected, or at least made public, I must say. And it's going to be almost 10 months or so. Okay, we are not yet okay ready with one vaccine, one material. So and what is the consequences? Or what are the consequences? We have lost so many lakhs of people from this world. Okay, we have lost our brothers, sisters. Okay, so many people around the globe. So if that material could have been December, it was December 5th, it was detected, December 10th, yes, take this material, ready for your deployment. Then probably, okay, this type of thing, the world would have been a different one today. So this time, why? We don't have data. We don't know. We have material. Yes, we have material, no doubt about it. The scientists are not going to get a new material from some other planet or so. So they will manage with the materials available in this planet itself. Maybe they will have to design it. They will have to see the combination. They will have to test them, test its efficacy, okay, test its power, its other properties, and then go for certification and deployment. So therefore, had we been blessed with some data, previous data, yeah, this material has got this material has got these properties, this has got this toxicity, this has got this reactive characteristic towards human body, this has got these characteristics of reacting with animal body, and so on and so forth. But we don't have. And therefore, just without testing, we cannot deploy any material in human body. So is the case with anything. Anything. I can have one material developed for, okay, it is very good for, say, like making LEDs. I cannot simply tell the manufacturers, okay, use it. So I have to get the certification, I have to prove its worth and so on. And for that, I need data. And that is the very essence of this material genome, like how we can have data, how we can design a new material by using previous data, by using different design mechanism, different simulation techniques, and we can bring down the time of developing a material and deploying the same material. So that is the essence of like a kind of material genome project. Okay, so these are like some of the things like coming from literature. You can always Google out this data. I have given the source also. So this was part of the like material genome initiative is the part of like US initiative. So all of you might be knowing US president has got some departments with them, like Department of Energy, Department of mm, other these things. Okay, so they department what they do. So they form a group of scientists. Okay, and they are given a task. Say for advanced manufacturing, they are given a group of scientists will be given a task. For advanced materials, a group of scientists will be given a task. Okay. For alternative energy, a group of people will be given a task. So like that. So US office of the US president. So they have different like specialized units or specialized group. So who will be working on this, and this is one such initiative, materials genome initiative by the office of the president of United States. Okay, and they came up with one white paper. So in 2011, okay, and they started that material genome project, or they call it material genome initiative. Basically, it is for for national security, as they say it, human welfare, clean energy, then next generation workforce. So if we have material data, all these things can be served very efficiently, or you can say with less resources, less resources. So for that, what we need digital data. We need computational tools. We need environmental tools, experimental tools. Okay, and this involves huge computation of data. So therefore, we need very advanced tools, very advanced computing machines, very advanced computing techniques. Okay, and the data is enormous. And once we can come out with some solutions, say one material, okay, which will help you in say the cells. Nowadays, this is a very hot topic. How we can have very fast charging cells. Nowadays, electric vehicles are coming, but then the charging of the vehicles are a big problem. So how far one vehicle can go in single charge, okay? So that will depend on its cell capacity or the material with which that cell is made of. So if we can have a material, very compact one, yet very long lasting, it takes very less time, less amount of time for charging, then probably we are contributing to clean energy. And why not? It is being used for human welfare only. So therefore, so these can have impact on everything, national security as well. We will be developing new technologies. We will be spending less resources in developing those materials. We will be spending less time in developing those materials. So it's nothing but national security. Okay, so it affects all, and the like credit of this concept, material genome concept, goes to Professor Jikui Liu of Penn State University of US. As you know, Penn State University is one of the leading universities in the world, not only in the US. Okay. So what it aims to, like the pace of discovery and deployment of the advanced materials. Okay. That between discovery to deployment, that time gap should be as minimum as possible. And if we can do that, then probably I will be able to sustain in the competitiveness in the 21st century, because it is of competition. Okay, nowadays, as you can see, even that .com companies. Okay, so if one website is promising you, okay, we will supply you or we will deliver you the material by within 4 days, the other company will say, no, no, we'll supply you within 3 days. Another will say, no, 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 within 2 days we will supply. So it is all about competitiveness and the time. Okay, time. They want to squeeze the time like anything. And whoever is having the least or the least time, okay, so he will win the race. And the material genomic project, so that aims to like reduce the new efforts in computation, new efforts in designing a new material, and new efforts to uh, uh, establishing its properties for deployment. Okay, so that's the whole crux of the things. Okay, will create a new era of materials innovation. Okay, as I said, like, so it offers opportunity to discover, develop, manufacture, and deploy advanced materials at least twice as fast as possible today. So this time compression, people are talking about time compression. Okay, it should be twice as fast. Means it is as per their like expectation. Even if it is twice, say 10 years comes down to 5 years, this is like huge. I have one example here. I will show you how one material led to another material, like development of or helped development of another material, okay, which took much less time. The first one took 8.5 years for developing, from the developing first stage to the deployment. The next one took only 5 years. So why? So that 3 years or 2.5 years, that sparing 2.5 years of effort, resources. Okay, so it is very crucial. And you think of like today's scenario. Why 2.5 years? Even 2.5 days. If somebody gives me a vaccine 2.5 days in advance, then people will be jumping on him. Okay, so that is the scenario, or that is the case. Genome is nothing but, if we just try to understand what is a genome. Genome is a set of information actually encoded in the language of DNA, and that is the blueprint of any organism. So similarly, if we talk about material, so there are some information, okay, so which will carry the blueprint of the or the characteristics of material. Okay, so in materials it implies fundamental building blocks towards a larger purpose. So that's material genome. So this initiative was like started in 2011, okay, and again in the United States. So this focus will better leverage the computational capabilities, data management, and integrated approach. As I said already, all these things I have already said. Okay. So data, when huge data will be regarding one material, there will be huge data. Then their functionalities and all these things, and how it will be developed, how it will be deployed. For that also, like it will be a kind of integrated approach for that. Develop the tool set necessary for a new research paradigm, which will, in which powerful computational analysis will decrease the reliance on physical experimentation. So if we see like why we need so much of time, that's basically because of the experimentation, physical experimentation. And until and unless we do the experimentation, we are not sure about the properties, we are not sure about the functionalities, we are not sure about its like consequences. So we need experimentation. And without experimentation, certification is not possible. And those experimentation like are very lengthy processes. But if we can have simulated like experimentation, if once that one material is experimented, and if we can like scale it up, or if we can like extrapolate it or use that same data for some other similar kind of materials, then that will be wonderful. And that may be possible but through some advanced calculations and advanced tools, analysis tools only. And that can reduce like 10 to 2 years, 20 years to only 2 to 3 years. The same like project which would have, okay, the result of which we would have expected, or okay, 10 to 20 years, now it may be possible within 2 to 3 years. So for that, like we have say genomic material genome things, how it came into picture. So here is a kind of like a pictorial representation. So this I have taken from Scripta material method earlier. So that is one of the highest ranking journals in the materials area, materials science area. Okay, so if we see from 1950 onwards until okay 2010, so this huge 60 years of gap. So at different point of time, people would have like developed different materials. Sometimes they have developed iron, they have gone to steel, they have gone to some other material. Okay, ferrium, then ferrium C50, C51 series, then ferrium S53, then ferrium C54, ferrium M54. So these are like some kind of like which same from we talk about iron age, okay, same iron, okay, ferrous material or the okay, uh, same ferrium or iron. So we are coming through different ages, okay, over the year, and we are designing new material in and around this like iron, okay, Fe, the basic building block, iron Fe. So for that electronic structure, if you see Fe is always Fe, okay, electronic structure will remain same. Okay, now we have developed this iron, okay, to give different functionalities, okay, with the help of other materials, processing it in other conditions so that it can give different functionalities. I will give you some this also, okay, examples also. Like with the same iron, we are getting today different alloys. So steel is an alloy, and steels, how many different varieties are there of the steel? If we talk about, there are hundreds of different varieties, and if you see the properties of this same these steels, okay, will differ so like significantly. Sometimes you will not, or it is difficult to believe that this is the same iron-based material, where we may probably we may forget that it has come from that same Fe. Okay, so like that, so there is a like timeline is like that for all material. It has got something like this, or some of the materials they were developed in between also. Okay, and they are now what they are doing is, instead of coming from say iron, from iron age, we are now alloys or very high strength alloys, or okay, heat resistant alloys, or so and so on. So can we design a new material today? We know all other properties of all the elements and all these things. Can we design a new material within say 2-3 months? I need these type of functionalities in this application. Okay, here one application is there. So landing gear, as you know, for like aeroplanes, landing gear is a very critical component. Okay, so material should have very high strength and very high, like specialized properties. So for that, material is to be developed. Simply iron will not do. So can I develop that material within 1 month? So like that, similarly for other say ceramics or ceramic based composites, polymers, the polymer based composites, can I develop it within few hours? So that is the like essence of going with this genome project, where probably all the data will be there. calculations, somebody would have done some calculation, somebody would have done some calculation, somebody, Austria, somebody have done this calculation, Australia, somebody would have done this calculation, US, somebody would have done this simulation. Okay, in India, somebody would have done this experimentation. So all put together, then can we come out, like all using together, all these data using together, can I design a new material within a very short period of time? So this is something like this. Okay, databases, different databases, and we can say, we can conceptualize this as phase 1, phase 2, and phase 3. Okay, with different like data, some like prototype data. Okay, from different calculations using different tools, like thermocalc is one very important or very significant tool used in material science, etc. Similarly, TICTRA and all these things, these are different tools and different experiments. Okay, so all these data being used for designing a new material. Okay, put in the database, see how the new material will behave. Okay, and for that, like for this concept generation, etc., also we need this data. Okay, so this material has got these properties. Okay, so now for this type of functionalities, I can design it this way. So that is the concept generation, and then design it, model it. Okay, model it, what is the percentage of this, what is the percentage of that, at what temperature, what should be kept, and all these things. Okay, designing, then sorry, scaling it up, process optimization. That is very important, process optimization. That is what I'm going to talk. Very important. We lose a lot of time in this phase. We don't know, we have developed a new material, but we don't know how to process it, and without processing, that material is useless. So this is very important. And then we have to, before going into like deployment, so we have to check with what is required in the in the actual field, and what we are getting, and whether they will match or not. So this is what one example I was talking about. So this is one blue dots you can see. Dr. Rajiv, is that slide visible? Data
Yes, sir.
visible?
Visible, sir. Yes, very much.
Okay. Am I clear? Everything okay so
Yeah,
far?
yes, you are audible, sir.
Okay. So
Great, sir.
these are the two materials, S53 and M54. These are the two landing gear materials. Okay, S53 and M54. These are two alloys. And if you see, like S53 took almost like from 2000 to 2008. Okay, it took almost 8.5 years. Okay, 8.5 years for developing and deployment to go to TRL 7. So TRL is, most of you might be knowing what is TRL, technology readiness level. So technology readiness level 6 is considered to be the pre-deployment level, and 7 is called the actual deployment level. Okay, so technology readiness level. So you would have started, developed the material here, TRL 1, then moving through different phases, testing, then designing, simulation, experimenting, and all these things, and we come to TRL 7. Okay, and that took almost 8.5 years. Whereas for M54, this is another material. Okay, this is another material used for, again, that landing gear and all these things. What is that? It started in 2008, and 2013 it was like deployed. So 5 years. Why? We learned from this. We use the databases, we use the simulation processes and all these things from this material, and we used here, and it took only this. So it is almost like you can say 60% of the time that the other one took. So it is a huge benefit. So in some cases, it may be even smaller. This is one of the cases I have taken. There are other number of examples you can see. So that's the advantage of material genomics. We are using the data. We are sharing the data. Okay, somebody would have generated the data, like say as far as the development is concerned, somebody would have analyzed the data. Okay, and they are being stored and they are being shared among them. Okay, and who will use which type of data for all those things also. Okay, you can have a kind of master database like crystal structure database. Crystal structure is known, crystal structure, but for how many materials in how many ways. So all these things, if all these things are available at one place, is it not very easy for all the users to use this crystal structure data straight away for designing the alloy, for designing the material, new material, for getting that, for simulating its property, for designing, processing temperatures, and so on. Okay, so that is what is being done. So database, central database will be there. So different like physical layers. So different small database. Say somebody will have like development data. Somebody will have design data. Somebody will have simulation data. Somebody will have experimentation data. All those things. Okay, maybe put in a big database. Okay, logical layer. Okay, people may be using this data for different purposes. Somebody will analyze performance, somebody will use processing test, and so on. So that's the huge advantage of this genome project. Okay, so these are some of the materials and databases. I don't think it is readable. I'm sorry I could not retype it and all these things. I have taken it from some research papers, so you can also see this in those research papers. It is not my own data anyway. But these are available in the public domain. But what I would like to emphasize here is, see, some of the like common materials database for metals, for the different chemicals, for different other glass, and so on. Okay, crystals. So there are and different names, and there are different like websites are being given. That means you need not to reinvent a wheel. Why we need to reinvent a wheel? Already this glass, regarding glass data are available in this domain, in this particular database. You go and extract it, use it for your own purposes, or use it for new material development. You will save time, you will save energy, you will save resources. So that's the whole like idea behind this material genome project. Okay, so different people from different aspects of these things, they can use this material database for processing, standardization, okay, networking, so for all kinds of purposes. Okay, so with this, I think I have finished my first part of this thing. I'm sorry, I'll kindly allow me to take some water.
Yeah, so we can break for 5 minutes, and later on we will
Not
rejoin.
necessary,
Not this
not
week.
necessary. For me, anyway, I cannot sleep.
Sorry, it is
and
that.
and most of the other people I don't know, like they may be sleeping only.
No,
They
sir,
don't.
I am listening to your talk very interestingly. I'm finding it
Is it
very,
interesting?
yeah, sure, sir. It's a kind of
Uh,
newer topic for me. So I'm listening it very interestingly.
yeah, why I'm telling is, see, afternoon classes immediately after lunch, even if it is a
Yeah,
classroom
yeah,
environment, almost 50% will be sleeping in the classroom itself,
yeah,
where
because of
teacher is
the,
in front of you, only 2 meters away from you or 4 meters away from you.
yeah.
But here, the teacher is 7,000 kilometers away from you. Okay, and you are on your bed. Okay, or on your like okay,
No,
living room.
no, we are
So
presuming everyone is on a chair and table. Like I am
okay,
in
just
office also.
on the lighter side. This is on the
Yeah,
lighter side.
yeah,
I just
sir.
I'm not underestimating any, or please don't take it otherwise.
Right.
Okay, all the participants.
Yeah,
Uh,
people are also writing. We are.
oh, is it?
It is an interesting session. We all are listening, sir. We are not in sleeping mode, so
Thank you.
yeah,
Very nice.
yeah.
Thank you. Okay.
You can continue, sir, whenever you feel like.
Oh, we can. I can start if you are
Yeah,
ready.
sure. Yeah, sir, sure.
Okay, I'll start. So as I said, like the other part. Now we will come to processing part. Now where is the like link? So that is a very difficult question. So probably um, Dr. Rakesh also asked me, sir, processing and genome, how it will be like both will be different or something like that. Then I said, even I don't know. So I gave on that day, I gave the topic. Rajiv was asking me, Rakesh was asking me, sir, topic. So I gave a topic, thinking that something I should speak different from microwave. Microwave, every day I'm working, every day I'm like doing research with my, right now I think 9 research scholars are there, 8 are working in microwave. Okay, so every day we are talking about microwave only. So let it be slightly different from microwave. And uh, I took it as a challenge always for every talk or everything. So I always try to put a new challenge on me. Can I do this? Let it be a talk, no problem. So can I do this? Can I now relate the material genome and this? How it can be? So far I have talked about material genome. I hope I was clear so far. And now the how to go from here. So in the previous slides itself, like at some point of time, I talked that how the processing, okay, processing test and all these things. Okay, that means for processing you need material data. Where from this data will come, or until and unless we process a material, how come this material will be used or will be deployed in the field? That's the very fundamental question. You can develop a material, fine, but you have to be like capable of, you have the capability of processing the material very efficiently. That too, not by somehow I have processed. I will give you some example of somehow processing that I am doing right now. Okay, because I am a researcher. I'm not an industry person. Industry person will ask a ready material. Come on, give me the ready material, which is like, okay, I can give me the process. I can use it. I can do this step one, two, three, and step, and I will get the material. Industry person will ask like that. But for me, it's a challenge. I have to develop those steps and number of steps. And while coming from step number 1 to n, in between I will have number of bad processing or semi-processed or iteration, all these type of data. And I don't have, if I'm working, I'm using a new material, I'm using a new method, so I don't have data. So now probably this material genome can help me. Okay, if I have the access to material genome project, or there's the database, different databases. Okay, so that processing time gets reduced. Okay, I'll tell you. So I'm publishing on this microwave drilling or microwave joining, microwave say cladding. So I'm publishing on this. Maybe some 80, 75, 80 papers I have published on these topics. But every time I had to generate my own data because there is no data, because these are new methods. Okay, although materials are not new, but that material, say steel, process in microwave, there is no data. I had to develop. I had to develop my own data. Say silica or say silicon carbide processed in microwave, data are there. I have used those data. I got benefited with that. My time, my energy, my cost got reduced. But for processing steel inside a microwave oven, I don't have data. People say, the others say, don't put steel inside the microwave oven. But I took it as a challenge. No, I should be able to do that, or I should be able to find out where that problem is there. Okay, I should be able to find out, simulate, and find out the data. Okay, why it is happening. So that is where that, like, this genomic information may be very useful. Now, if I create a database, if I put these things in a database like this, then when Dr. Rajiv will be working, when some of you, so 100 people are listening to me, okay, some of you will be processing. So probably you can directly, readily, you can access this data. Oh, yes, this is there. So A.K. Sharma and his group did this, so I can directly use this. Okay, so this can be done from the journal data also, but then again, it is a kind of like lot of process, lot of these things are there. But here, as you can see, it is probably you can have direct access. But how that mechanism will be done, how it can be made useful or made like workable, please don't ask me. Probably I am also not aware at this stage. Like only it is my thought process. Thought process. Had it been, wouldn't it have been very useful, very like time efficient, very resource efficient? So because without processing, a material is meaningless. Its processing is also equally important. And new generation materials, new material, whenever a new material is being developed, so obviously the old processing techniques, 100% it will not apply. You will have to develop its processing technology also, or the processing techniques also. But all data may help. It directly as it is, it cannot be employed. But the history, the data, the simulation process can definitely help us. So that is where material genome approach can help us. We can reduce tremendous like time. Like I was talking about that S53 and M, what is that? The landing gear M54 and S53, that the examples just now I have given. One took 8.5 years and one took only 5 years to bring it from the development till the deployment. So that is a huge like gain. So similarly, if this also can be, many other things also can be done, uh, then our effort will be, our resource will be uh, reduced. Resource requirement will be reduced. So it may help in time as well as in economics. Okay? So this is the link between why we should learn material genome and why it cannot be like taken as only pure material scientist perspective only. Okay, the materials processing people also, okay, manufacturing engineers also equally could be beneficiaries, okay, equal beneficiaries for this materials and genome uh, data, or material genome approach. Okay, so with this, probably I will move on to process, which is very dear to me. Like I have developed this process from scratch. Of course, another group uh, in the world, okay, Tel Aviv University, Professor Zarvi. So he has developed this to some extent at the very beginning, but his process was, you can say, not exactly like thermal drilling. It was semi drilling kind of, semi thermal, semi mechanical process. I will show you. But today, what we have like microwave drilling, it is a completely thermal based process. It is like, you can say, it is like laser drilling, where only material ablation is taking place. Okay, so in this microwave drilling process also, only ablation is taking place. There is no role of mechanical force or mechanical um, effort is required. Okay, That is where we have done our thing. Okay, we have patented it also. So this was a work we started with, like with Baba Atomic Research Center, Bombay. So Department of Atomic Energy sponsored this work. Okay. So you can say this is a microwave drilling is a non-traditional machining process, because here the traditional tool contact is not there, or even if it is there, it is a limited contact, or it is not there. And the important thing is here mechanical that hardness principle in conventional machining, that is material tool material should be harder than the work material. That principle doesn't apply, and it is basically based on the thermal ablation process, like the way laser is being done. Okay, and here instead of laser, what we call is microwave metal discharge. So that work here, like in your EDM, electrical discharge machining. So most of us, like I believe most of us are mechanical engineers or production engineers. So we know how does laser beam machining work, how does EDM work, okay, where only thermal energy is required for ablating the material. So here, instead of laser energy, we put microwave energy, and the process is microwave metal discharge takes place, okay, and then that thermal energy ablates the material, and we get a kind of material being processed. Okay, so these are some of the parameters. So many parameters: discharge medium, material, microwave power, frequency, exposure time. Then discharge, what is the viscosity of the medium? Okay, if it is air, it is a different kind of discharge will take place. If you replace air by some other gases, then the different kind of discharge will take place. If you replace that by vacuum, like only vacuum is there, then different kind of discharge will take place, and accordingly that melting will be, or evaporation or ablation of the material will be different. Okay. Similarly, not all material you can do in the similar fashion. For a glass, it is a different technique, different kind of behavior. Then for steel, it is a different kind of behavior. If you put a ceramic plate, again it will be a different kind of behavior. We need material genomics. For all these things, we need data, and that can help us. Okay, so right now for me, everything is new. So we don't know which material will behave under this material discharge condition in what way. Okay, there are some papers, so they have seen for different applications, like from chemical processing point of view, from reaction point of view. Okay, they have seen some of the cases, but from drilling point of view, where tremendous energy is required to remove the material for ablating. So that is a totally different distance. Okay, and particularly I have tried metal recently. We are working on metal. So people have been working on other materials. Plastic and polymeric materials are nothing. So it is anytime it can be done. Okay, then glass is challenging because it cracks. So glass, it needs lot of careful handling because of the stress generation, thermal stress and thermal cracking. Okay, so that also I have done. I have been working with. And metal people say don't put any metallic material inside microwave oven. The manufacturers, while selling their microwave oven, they put one big red slip there. Don't put any metallic material inside this oven. So metal is even dangerous. But today we are regularly doing these things with metal in the same microwave oven what you have in your kitchen, same microwave oven. with same power capacity, with same frequency. Of course, microwave, whatever for commercial use or home use, whatever ovens are there, so these are at 2.45 gigahertz only. So that way, this frequency, what I am talking about, this frequency is also fixed. Okay. So I am using those things, and once we can put all these data in the form of a database, then others can access, and it will become a kind of genomic advantage for others not to try again. So this is what I was talking about, like Zerbi, Tel Aviv professor. So Eli Jarvi. So he was the first person who tried this drilling. But what he did is like he could soften this material, and then he applied mechanical force. Okay, he applied, you can see here. So application of mechanical force. So he could pierce it. He could pierce the material down. Okay, so he like developed one hotspot. I'll tell you what hotspot is by microwave discharge. Okay, but it was not sufficient enough to create a hole here. That hole was created by some kind of application of like forces. So hotspot is like it is based on thermal runway um, concept. What is thermal runway? Thermal runway is so you apply microwave for some time. It will slowly it will like absorb um, energy. That energy absorption is very insignificant, or you can say the rise in temperature. Energy absorption, we are like converting it in terms of temperature rise. With time, it is very insignificant. If you see from here to here, 10 minutes or some 12 minutes, it is very less. Only 200 or 300 degrees centigrade only temperature rise was there. But immediately in the next second, say 13th second, the temperature was something around, okay, 1500 or 1400. So how it happened? That means there is a particular temperature at which like the material absorbs the energy very much and the temperature goes very high. That is the call hotspot formation. Like now that spot has become a kind of source of energy. Temperature has okay gone up like very much, and we can say so the material has or it is a condition of thermal run away. So it is not simply increasing, but it is running away from the normal. Okay, so it is called the thermal runaway. And when this happens, the material gets softened very much. And if you press it little bit with your some application of mechanical forces, so the material will get like dislodged from the position, like this position. Okay, so once it goes to the thermal runaway condition, so you applied little bit of force with this say tool. So this is the tool. Okay, and then the material will be removed from this, and this hole will be created. So this is what was like done by Zarvi, and he did this type of like holes in glass, borosilicate glass and soda lime glass. Okay, and always Professor Zarvi questions me, your holes look like very bad. My holes look like very clean, neat and clean. So he used to like question me like that. But what he is not telling is the skill. What is the skill, and what is my skill? I am showing the holes or the damaged zone under scanning electron microscope, which is say 2000 times or 1000 times enlarged, and his scale is like just as it is. So this is 2 mm, 2.4 mm, 2.4 mm, or say whatever. Okay, and at this scale you will look like you will see everything is like good only. You enlarge it by 1000 times, not 1,000 times, 500 times, you will get hell lot of like defects, hell lot of defects here. Okay. So anyway, so I am not trying to undermine Professor Zarvi's work. He's still the pioneer in this field, and he has shown the way that yes, there could be another method for drilling, material drilling, and we are trying from a different perspective or with different uh, technique, okay, different approach. So this is again some other people tried again his group only, okay. Then came 2012 onwards, we tried in our laboratory. I joined IIT Roorkee in 2006. Then I started with microwave metal joining. Some people were laughing, why you are taking metal? Metal anyway should not be used with microwave. So again, it became challenge for me. Okay, let me try. I tried, and I got a patent in that uh, joining of metallic material by microwave in the same kitchen microwave oven. That patent was granted. Then I joined Inconel, I joined Steel, I joined MS, I joined MS to SS stainless steel, I joined stainless steel to Inconel, and kind of various means similar as well as dissimilar material I have joined in this microwave oven. So that was broke. Then I used microwave cladding, so that was also patented. That was again new data. So nobody did that so far. And we were the first globally to uh, use microwave energy for developing cladding. Okay. Sorry, just a minute. Okay. Then 2012, I got one very enthusiastic student, Tito George. He's from Kerala. I don't know. Today he may be listening also somewhere, somehow. I'm not sure. Okay. So I have lot of good wishes for him, lot of respect for him also, in a sense that he was my master student, MTech student. He was so enthusiastic. Like if you tell him to do 50, he will do 100 always. So something like that. So he was so over enthusiastic. Sir, I will do drilling. Sir, I will do. I said it is nobody has tried. Nobody data are not there. Be careful. He removed the microwave door and all these things. He brought some okay, means he did lot of things, like probably that was not correct, but without informing me also, he did lot of things with his enthusiastic mind, which was probably health wise also it was dangerous, but fortunately nothing happened. Okay. And the good thing is he could give a kind of daring effort or for starting this process, microwave drilling. He tried with different way. Okay, some like using mechanical force also, like spring loaded drill bit, and then using some other material to soften this material. Okay, so like that he did, and he got some limited success also on different materials. Of course, at that time we did not try, or Tito did not try metallic materials. Uh, he tried so many things like wooden wood. He tried bones. He tried ceramic plates. He tried glass plates. Like uh, n number of materials he tried. And therefore, whenever I talk about drilling, I always remember Tito very much. And later on, of course, when we filed the patent, it was on glass. Um, okay, we could drill glass, but I made sure that Tito's name should be there as one of the inventors. So I put his name as one of the inventors for his drilling patent. Okay. So this is the drilling process. So where this is the tool, and this is how that plasma channel is formed, or this discharge, what I was talking about, microwave discharge that takes place. This is the metallic tool. Okay, and this is where we are keeping the say target material for drilling. Okay, here we are putting metallic workpiece, and sometimes we put glass or whatever the material we want. So this is fixer and all these things. This is inside the microwave oven. You are seeing this view inside the microwave uh, oven. So how it happens? Like, what is the physics of this? So let me very quickly talk about this. It is, I think, only 10 minutes are left. Okay, very quickly I will go through this. So when microwave is like subjected to a material, so what is the material property? So again, we go back to Xenome. So material property, crystal structure is there in the database. So we know what is the crystal structure. We know what are the characteristics. So the Xenome will help here. Okay, we need not to go for new. Okay, these things. Then depending on that, those properties, how the field will be generated inside this material. So that will be determined by the material characteristics. And as the microwave like strikes this material, okay, either it may go through this, or it may get absorbed inside this, or it may get reflected. As you can see in this dotted line, it is reflected. Okay, so in glass, etc., it goes through this. In some of the material, silicon carbide, etc., or water, it gets absorbed inside this. It gets absorbed in this, inside this. But this is metal I'm talking about. So in this metal, what happens? So it gets reflected, say, from a very small skin. So this is something around a few microns. This ds, what you can see, this ds is only few microns. And the microwave gets reflected back, okay, from this skin itself. So inside nothing happens, and this is dangerous since this is getting reflected. So it can cause harm to the equipment, it can cause harm to the human being or something like that. So that's why you also, please, although you are listening to me, please do not get into this adventure that if AK Sharma can put, I can also put. So my request is 100 times I'm requesting, please do not try that way without having proper information. Okay, I could also do this only few years of experience and few years of learning only. Okay, so you please, nobody should try this without any further knowledge or distance. Okay, so at the corner, so when the microwaves hits this, okay, this metallic surface, then there will be charge distribution. Okay, some charge will be aligned like this, and if you see the corners, so there will be more charge density, and here because of higher charge density there will be some sparking. This is what we can see when we keep inside microwave oven some metallic material. There will be a lot of sparks. It is like you can say crackers. I used to have some videos earlier. I used to show. Nowadays I have stopped showing those videos, etc. So that those are those sparks, and that those sparks are created because of this. Okay? So that is actually those charge is like the deflected electrons, and if we try to make it more intense, then this will create a kind of discharge that is called microwave metal discharge. Okay? And how it happens, just let me tell you. Okay, so this I'll skip. So the microwave is like, it is changing very fast, 2.45 gigahertz you can say. So 2.45 gigahertz means cycles per second, this many times. So it changes. So microwaves has got two components, one is electrical and one is magnetic. So if we consider the electrical component, So in this one cycle, it changes from positive half to negative half. And if I keep the one concentrator or one tool there, metallic tool there, then the charges induced in that tool because of this microwave field will be something like this. And in the negative half cycle, it will be different. It will be different. And if it is a kind of blunt tool, it is something like this. And if it is a sharp tool, it is something like this. Okay. So this is what happens, and this causes this sharp edge. If you can see, electron density is more, so this causes discharge. We'll see what is the mechanism of this. So this is a tool or the metallic concentrator, so which is subjected to microwave, and microwaves is creating a field, okay, where at this tip that induced charge density is more, and therefore there will be a kind of plasma generated in this. So that will cause the atmosphere, okay, to get ionized, and a plasma will be created. And that plasma will be hot plasma. You can see this plasma. This plasma is hot plasma, and this hot plasma will ablate this material from this zone. And this tool will advance. This tool advancing can be gravity based, or this can be, nowadays we have developed system for automatic feedback also, automatic system also, or maybe pulse based also. We can control this feed of this tool, feed rate of this tool. So this is the mechanism how it like drilling does take place. So this shows like how exactly it happens. So electrons get accumulated here. They ionize this environment around this tip. This is the tool tip. This is the tool, or also we call that concentrator, because it concentrates the electron or the charge at its tip. Okay. And microwave is under the inside the microwave oven. So microwave is coming, and under the influence of the microwave field, so these electrons are getting accumulated here, and it is ionizing the atmosphere here. And when it crosses some threshold, so these electrons, okay, jump from here and okay goes to the workpiece. And here workpiece is again metallic material. We are putting stainless steel or something like that, okay, copper or whatever, okay. And therefore, so they jump from this tool material to this, and this causes this plasma, and this causes this type of things. You can see this and this. This is what experimental result. This is our theoretical postulation. Okay, this is it inside our own picture. So this we have tried to like see it from different like angle, different. Oh, already 4 o'clock. Dr. Rajiv,
We have some time, sir. So we can extend
we
it
have
up
some
to.
time.
Yes.
Okay, maybe another 5 minutes, 10 minutes.
Sure, sir. 5 to 15.
Yeah. So we have seen these things phase wise: phase 1, phase 2, phase 3, phase 4. So, like in one case, the electron cloud or the concentration takes place. Then the breakdown of air, just as I have shown here, electron concentration takes place. Then breakdown of air. Then plasma channel forms, and then because of that hot plasma channel, the material gets ablated. So this is how the things or situation of events that do take place. So this is the actual tool. This is the actual tool. Okay, pointed tool. This is the magnified view. You can see. Okay, this is the tool. So this is where the charge gets accumulated. This is how we are putting it inside the microwave oven. This is the normal microwave oven, whatever you are using in your kitchen. So these are like two like materials we have tried: galvanized sheet, ZS sheet, or stainless steel sheet. Okay, for that different types of power we have used something around 700. So 700 is the rated power, but actual power will come something around 550 to 600. Okay, the 700 is the rated power of the equipment, but we have measured it, we have calibrated it with other mechanism. So actual power getting absorbed is something around 600. So we used to keep a tool work gap of 1 to 2 mm. That is why at the beginning itself I said this is a non-contact uh, type of like machining. This is non-conventional machining. Okay, so we are maintaining a gap of 1 to 2. Sometimes we allow it to touch also. That is also another thing is there. Okay, but generally we keep 1 to 2 mm gap. Okay, and exposure time is only 40 seconds to 60 seconds or something like that, 1 minute. And the metal thickness of say something around, what is that, 0.5 mm, so gets like, okay, ablated 1 mm, 1 mm. So we have tried to like characterize those holes in terms of overcut, and at the entrance of the seat, how the hole is looking like, at the exit of the seat, how the hole is looking like. So all those things we have like tried to see. From this side it is entrance. Okay, this is entrance. This concentrator is here. So how this area is getting affected. This is the exit. So how this area is getting affected. What is the overcut here? What is the overcut here? Circularity here, circularity here, all those things. So these are part of like our research. So we tried those things. So these are something like see, circularity at the exit, circularity at the entry. Okay, entry and exit. Similarly, diametrical overcut at the entry and the exit. So all these things we have seen. Okay, and we have found if we allow the material seat to be for only for 40 seconds of microwave, then we get undersized hole. But if we use 65 seconds, we get oversized hole. So that means the time of exposure has got some influence. We need to optimize it. So as I said in the material genome problem, so optimization data, very important. So today, if I optimize it and if I find it, yes, 60 seconds is the optimized time. So tomorrow, Dr. Rajiv should not again do the same thing. So he will be using it directly using material genome. Okay, data. So similarly, like why he is not using 65, 67. So again, he need not to do like the experiments to see what will happen in 70 if he goes to 70 seconds. So it will be there in the material genome. So it will have, okay, if I go to exceed by this amount of time, then circularity will be bad. Its overcut will be increased. Therefore, I am not going. Okay, or I am not using 30 seconds also because I will not get the actual dimension of the hole. So this is the kind of hole we are getting. Okay, and this is the profile. So some more are there. I'll show you. Then we have seen the tool wear also. There is a substantial tool wear is also there. We could identify tungsten peaks here in this. So in this material, whereas there is no chance of any tungsten, but we could identify some tungsten. So this tungsten would have come from the metallic concentrator which was having tungsten. So that way we try to like correlate the things. Okay. So these are some of the micrographs. So these are SEM data. So you can see this is 0.5 mm. This length is 0.5 mm. So you can see the enlargement. So our holes are also not that bad in comparison to Professor Zadvi. And please remember, these are in metal. Okay, these are in metals. So we have seen that entry side, see entry side and this exit side, both side we have seen. Okay, so some characteristics are there. Entry side generally okay, exposed to higher energy, but exit side lower energy. Okay. Similarly, we have seen for like SS304 also, that was GS galvanized sheet. So for SS sheet also we have seen similarly exit side and the entry side. Okay, both sides we have seen, and we have found that circularity in SS is better. And entrance and exit overcut wise, if we see, sorry, CS it gives like maybe more stable kind of performance. And if we see the thermal damage zone, that also ZSC it is better in case of while compared to SS. But so if with further like optimization, probably we may get even better kind of result in this case. Okay, but at this moment, let me tell you that this process is not error free. As you can see, there are circularity problems, there are like overcut problems, there are some heat affected zone problems. I'm not like that type of researcher who will tell that my process is the best in the world. Then my learning will be stopped. So I will have that complacency, but I don't want to do that. I want to see what are the problems in my problem, so that I can perfect it. I can do a better job. So tomorrow I can improve my process. So that's what my objective is, and I wish all of you also to have similar kind of attitude towards research, so that then only we will be able to further our research or better our research day by day, not by like hiding our weaknesses and not telling others about the problems of our weaknesses. Maybe in that process, somebody may give me advice also. Sir, you do this, that way. Okay, Professor Sharma, you try this. So I may learn. So that's the thing. So these are some of the holes we have done. So probably, I think there are a lot of data. I don't have time, that much of time. I have another important meeting. So I have to meet one target today. I gave time 4:15, thinking that 4 o'clock it will be over. But anyway, now messages have started coming. So I will go, but not before interacting with you for a couple of minutes or for a couple of questions.
That's
So similarly, we try to record this process also, what happens when this is going on, like discharge is going on, how it looks like. We wanted to have the recording of the things, but our ordinary camera cannot record this good as good. So this will be something like this one. Okay, we have recorded it, but I'm in the process of developing one setup having something 50,000 frames per second recording, or 1 lakh frames per second recording, that capability. So I have already ordered camera. So I'm in the process of developing that setup. So we want to see, so that 1/50th of like second, what happens in this, okay, inside this. Then probably it will give very interesting results, much more information. And probably in the next talk, if Rajiv gives me sometime some chance, then again I will be able to share some more data, beautiful data, or much more uh, advanced data. So we tried all these things, but these are with our own conventional camera. But the progress, work is in progress with high speed camera. These are with our conventional camera. Okay, so these are with conventional camera. So to conclude, so probably what I must say, so I have nothing to conclude on this. Material genomics I have not worked, material processing I have worked, so I have shared few things. Okay, but it is not like material genomics should be only for design of materials. Its boundary can be enhanced. That's what my feeling is. That's what I have understood by studying genomics, and probably you can have better conclusion, better study on this topic. One more thing I would like to share is, like, no data can be bad, no research output can be bad. Result may look like bad, please remember. You may have a lot of heat affected zone, looks bad, Doesn't matter. Doesn't matter. That is where I have seen that bad. That's why I will be able to these things improve that. So when we sent that with a lot of heat affected zone, these kind of things to one journal, very leading journal, one of the referees said, this looks very like haphazard or very dirty kind of things. Another referee said that is where his research is. So it's a kind of like the first referee also, he did not say these are bad, but it's looking bad. Okay, but immediately the other referee said, no, that is where his research is. That is what he is trying to find out. He is trying to show the world that this is what happens. So please keep these things in mind and let's work. And more work will generate more and more data, and we'll be able to contribute. Okay, let's enrich material. These are some of the papers, some of our papers. I'm showing our papers, okay, which we have published over maybe last few years, okay, like 4 or 5 years, or five years or so in this field. I'm talking about. I'm not including others like cladding, joining, and all these things. I'm not including casting. Casting is another area we have developed. We have put patent also. Okay. Only in drilling, some of the relevant papers. Thank you so much. Thank you for your pleasant hearing. Okay, pleasant listening to me. So 1.5 hours, 1 hour 40 minutes, I think. Okay.
Yes, sir.
Thank
Thank you
you
so
so
much
much.
for the talk. Let's take some of the queries that we have compiled through Google form. Uh,
Oh, yeah.
so one of the participant he wants to ask, what about controlling of macromolecular collides? How can we
Yes.
assure that? We
How
need
can
to
we?
know
How
how
can
can we
we assure?
how can we assure the controlling of macromolecular collides?
For what?
Uh,
Macromolecular collide. So this is macromolecular collide is it is a very complex phenomenon. So it will have in different boundary, it will have different meaning. If you talk about like liquid based system, liquid solid system, liquid system, then meaning will be different. And in all these cases, in a vapor system, you are talking of, please remember, molecule can be in vapor state also. Okay, so it will have different meaning for different system. I don't know for what you are talking about. Okay, and what to ensure. So if I need to ensure collision of two like solid particles, then I should have a different system. If I want to ensure liquid molecules to collide, gaseous molecules to collide, so they have different systems. And as you know, like random gaseous molecules will have random motions. They in fact they keep on colliding each other. Okay, and if you want in a controlled manner, then for that you need to have a different system. Like for nuclear fission, so they have a controlled controlled collision of controlled bombardment of um, this um, atoms. Okay, so I don't know what kind of questions you are trying to. Another, Rajiv,
yeah,
do we have any other?
yeah, we will quickly take a few more questions. Uh, what are various certifications of the new material continuum?
Yeah.
Uh,
So,
what he
yeah,
wants to ask, I
certification.
think. Yeah.
Yeah, there are different certification systems are there. Like ASM certification is there. Okay, then different ASTM they gives testing certificate. ASM they have certification system. So there are agencies or there are organizations.
Uh,
Next.
so, we also have one question. Uh, Wear resistance, corrosion resistance, and hardness comparison of aluminum alloy 6082 with aluminum alloy 7075, which is better? I think this is a too specific a question, and one can easily find out from the properties which are available
Exactly.
at a number of sources online
Exactly.
also.
Yeah, yeah. So these are specific things maybe pertaining to his research, his or her
Yes,
research,
yes,
and very less related to what we have spoken today.
yeah.
Okay, they can
Then
find out.
there is one
Yeah,
more question: how density and viscosity affects
yeah.
microwave discharge?
Yes,
I
yes,
mean,
yes. So this is very relevant question. So density, yes. Say we have used different materials. So glass we have used metals. Metals also we have used CS and SS we have shown. Then for the discharge, as you have seen, discharge is not taking place in the metal inside the metal. Discharge is taking place in the dielectric, which is air in this case we have used. Now we are trying to change this density or the like medium or characteristic of this medium, okay, uh, to control that uh, discharge. So when we change the uh, dielectric, that means we are changing its density or whatsoever its properties. Okay, so we have changed the air, and we have submerged it inside some other materials. Okay, other dielectric materials. Okay, and then we have found that the discharge is not the same. With higher density, the discharge gets, you can say, attenuated. Okay, or it gets localized in a smaller area than that of wider area. So therefore, what we could find out, like although we did not correlate from density point of view, because we are trying to see the how we can get a kind of smaller impression, like reducing the overcut. Okay, so what we have found is higher density materials like reduces the spread of the mm, discharge.
uh,
Yeah.
these are the
Any more
questions.
insight?
Sir, not many important questions. So there are.
Yeah.
So we can, I think, close here.
Yeah.
And
Fine.
in closing, I wish to express my gratitude toward Dr. Apurva Kumar Sharma for the illustrative and inspiring talk wherein you talked about the fundamentals of material genomics and research aspects related with microwave material processing. And I must say it was done in a very lucid manner. Well, eventually, on behalf of organizing team, would like to once again thank you from the core of my heart for accepting our invitation as one of our speakers and taking time from your busy schedule. We are highly indebted for this act of kindness, sir. And we certainly hope to have interactions in near future by offline mode, preferably. And
Thank
looking
you.
forward.
Thank you, Dr. Raju. So
Yes.
how many participants were there at the peak of this?
Peak of this, I guess more than 60 were there.
Okay, very nice,
Yeah.
very nice. Thank you, thank you for
Th-
your kind words.
Thank you
So
so much.
shall we stop? Yeah.
Yeah, sir. We can exit. Thank you so much, sir, once again.
Okay.
So, dear participants, thank you for joining. We will meet again for tomorrow's first session that would be taken by Professor Gaurav Manik again from IIT Roorkee. See you tomorrow then. Thank you so much.